Started with our announcements. First of all, welcome to our session, which is Mercury Inside and Out. I am one of your session chairs, Lauren Joswiak. My other session chair is Harry Hiesinger, and our moderator is Isaac Narrett. Our session is going to follow the standard timeline, so we'll have this 5-minute introduction period to allow our Zoom participants to join. We will then proceed with talks in 3 blocks of 4 10-minute talks, followed by 20-minute panel Q&A. We would like to ask our audience members in person to silence your cell phones and other devices. And when it comes to the panel Q&A, if you could please proceed to the microphones. We have 2 of them up here at the front. Please state your name and affiliation, and then to which speaker you are directing your question. For our remote audience members who were very eager and logged on exactly at the start, we'd ask you to submit your questions via the Zoom Q&A function. You will not be able to unmute and ask in person. Our moderator will read your question in the room. We have a couple of Dwornik talks in this session, so if you are a Dwornik judge, please keep an eye out for that and remember to actually fill out your judging form at the end of the day. As a reminder, if you have not signed up to be a Dwornik judge, but you would like to be a Dwornik judge, you can do that using the many links that were emailed to you. Or if you don't have one of those links, please come see me after the session and I will help you get signed up for that. As a reminder, we also have an associated poster session tonight, so please go see the rest of the great Mercury Science posters that are going to be presented this evening. Okay, well, if that's the case, we are going to hold for 3 minutes so that we can keep exactly on time. And our first speaker of the session will be my co-chair, Harry Hiesinger. So I'll let him get over to the podium. While he's transiting, a note on time. So for speakers, you will have a countdown clock at the podium. When it gets to 2 minutes left, you will start to see a yellow light. And when you are out of time, you will see a red light. And if you keep going over time, I will stand up and look very cross with you. So please do not let that happen. Can we get some of the smooth jazz back for our next couple minutes? Fantastic, thank you. Okay, can we bring up the slides for the first talk, please? Okay, so again, thank you everyone who has made their way in. Welcome to Mercury Inside and Out. Our first speaker is Harry Hiesinger, who will present first observations of the Mercury radiometer and thermal infrared spectrometer, MERDIS, of Mercury. Overview of preliminary results from flyby MSB number 5.
Thank you, Lauren. Good morning also from my side. So it's really a pleasure here to speak on behalf of the entire MERDIS team and present to you some of the very first interpretations and also some of the data, of course, that are necessary for these interpretations from a flyby that we had at the beginning of December. And the Mertus team, as says here, is the Mercury radiometer and thermal infrared spectrometer, and it's on board on Bepi-Colombo. So let me just remind you of what Bepi-Colombo is. Bepi-Colombo is a very large ESA JAXA-led mission that is on its way to Mercury since 2018. We will arrive in 2026. Some of you might have heard that we were supposed to arrive in 2025, in December to be more specific, but we have some issues with the electric propulsion system, and the consequences that we will arrive there about 1 year later. You can see the spacecraft is a fairly complicated group of spacecrafts, actually 4 tons above. We have the transfer module with the solar panels and the electric propulsion system. Stacked on that is the planetary orbiter. On top, we have a sun shield, and this sun shield houses the JAXA contribution, the magnetospheric orbiter. On the way to Mercury, we did 9 flybys altogether, 2 at the moon, 2 on Venus, 1 on Earth, and 6 on Mercury. And so it's going to be flyby number 5 at Mercury that I will report today. Once we get into Mercury orbit, the planetary orbiter that houses the Mertus instrument will be on a 480 by 1500 kilometer orbit. We will have a, roughly speaking, 1 year science phase, but we're already talking about an extension phase. And of course, you can see that there are plenty of instruments, 11 altogether on the MPO. So let me talk a little bit about the cruise configuration. You see here the stack of the spacecraft, and down here in the lower right, you see the planetary orbiter looking at the bottom at the instrument panel, where all the instruments basically have their port that points towards Mercury. And as you can see from this orientation during cruise, the planetary orbiter is oriented such that all these instruments are actually blocked from observing Mercury. However, Mertus is in a special position because we sit right at the corner of the instrument panel side and the radiator side, which faces to the left here. And the instrument is shown up here. So we have 2 ports. One is the planet port, where we usually observe Mercury with. And then we have the space port that we nominally use for calibration, but because it's pointing towards Mercury during the flyby, we could also use the spaceport to observe not only Mercury, but we also used it already on Venus and the Moon. That required, of course, a complete reprogramming of our observation sequence, the observation procedures and so forth, because when we left the planet, ESA was not allowing us to do any observations, but on the way towards Mercury, they decided, oh, wait a second, we have a couple of good opportunities to do observations. And so on the fly, basically, literally, we reprogrammed our instrument to do observations through the spaceport. This is the instrument. Again, the planet baffle here, the spaceport there. Inside the instrument, you have 2 additional black bodies, one at 300 Kelvin, one at 700 Kelvin. You have a rotating mirror, and so you can basically calibrate your observations from Mercury with 3 calibration sources, the 2 black bodies plus cold space that we observe through the spaceport. Mertus consists of 2 parts, one spectrometer part and one radiometer part, about 3 kilograms heavy, 10 watts of power necessary. And I'm showing here the objectives that we are trying to accomplish once we're in orbit: surface composition, mapping of the surface mineralogy, identification of rock-forming minerals, and of course also temperature variations and thermal inertia. To understand the data then accurately and as well as possible, we are running a very comprehensive analog spectral program here, both at the PI institutions in Berlin and in Münster. You see pictures here. We investigate in the lab space varying effects. We simulate them in many different ways. Of course, we are also looking at minerals at Mercury relevant temperatures. This is really important. That was a steep learning curve that the team went through. Doing measurements in the lab at room temperature just does not cut it. Okay, so we have facilities where we can heat our samples to mercury relevant temperatures. We can study, and we do study, mixtures under different viewing geometries, under different grain sizes. We look at analogs, we look at synthetic material, and in parallel to that, we also do some thermal modeling, of course. At the lower bottom, I show you the abstract numbers of colleagues of mine that will present either following my talk or during the poster session. So I encourage you to go to the poster sessions because you will see a lot of more detail that I can simply not cover in this talk. All the data that we produce in the lab are also stored in a database. We call it IRIS. It's publicly available. So if you want to know how a thermal infrared spectra of a pyroxene with a certain composition, with a certain temperature, seen under certain viewing geometry and grain size and so forth, looks like, then you can just simply go there. The database is fully searchable. You can get an immediate spectra of the sample. You get some geochemistry background analysis that we did. You can combine different spectra and so forth. And what I'm showing here is sort of a new interface that then will be available publicly in about April. And see Thomas Heyer for details on that. And we also will put our data from Mercury into our muted database that was originally developed for Mars and also for the Moon. But nowadays we also have Mercury data in this database. And again, you can find Thomas to show you some more information about both the databases here. Okay, let me speak a little bit about the flyby. You can see we had several flybys at Earth, Moon system, and Venus, and then 6 flybys at Mercury. Most of them were fairly close, about 200 kilometers from the surface, because we can only look through the radiator part of the spacecraft. These are flybys where we could not observe Mercury because Mercury would emit so much energy that would hit our radiator that the spacecraft would get too warm. So this radiator was facing away from Mercury, and with that, we could not observe Mercury during 5 flybys. However, the 5th one, where we were far away, about 40,000 kilometers, gave us the opportunity to look at Mercury. And what you just saw here is basically Mercury drifting through the spectrometer slit here. We were approaching Mercury from the day side, so we had very good observation geometry, and I will speak to that in just a second. So here's actually the data. I'm showing here the coverage of the flyby in radiances. So as I said, we were about 40,000 kilometers away. That results in a pixel resolution of about 25 to 30 kilometers. We gathered about 1.4 million spectra, and the phase angle was very small, 4 to 6 degrees, and that's very nicely complementary to the observation geometry that Messenger, for example, had. And you can see there's, of course, this latitudinal trend in radiance. That's completely normal, but you can also see fine-scale structures, and I'm just pointing out here one example, Basho crater that Solmaz Adeli will talk about in more detail. We measured temperatures, of course. We have a radiometer that sits right and left of the spectrometer slit. So 2 channels, if you will, A and B, that operate at different wavelengths. Nevertheless, you can see that the brightness, maximum brightness temperatures of both channels are fairly consistent and fully in the range of what is expected. We are at about 180 degrees longitude, so at one of the hotspots of Mercury, where we expect about 700 Kelvin. So these temperatures are consistent with each other and in the expected range. You also see some bump in the frontier. We interpret this as stray light, probably from the radiator fins. Remember, we were never supposed to use this port to observe Mercury. It's just a unique opportunity. Okay.
Can you please wrap up, Harry?
Yep.
Thank you.
Okay, so then we have the brightness temperature that Mario De More will present, manipulated a little bit, smoothed, and took out the latitudinal trend here. So what we see is basically differences in the brightness temperature between the floor of Tolstoy Basin and also the Goya Formation, the ejecta blanket, the very dark ejecta blanket. And so our interpretation is that the signal that we see is sort of a complex interplay between roughness, thermal properties, grain size, and also composition. And then we did some thermal modeling. On the left side, you see the radiance at 8.6.
We're really going to have to move along. Sorry.
Okay, sorry. Okay, that was quick. I apologize. Okay.
Okay, we're going to move along to our next talk. And for all future speakers, if you can go up to the AV stand a couple minutes before your talk to get mic'd up. So our next speaker is Adele, Bepi Colombo's fifth flyby, early MIRDIS observations of Mercury surface variations.
Thank you. Good morning, everyone. I'm going to continue on what Harry just explained about the fifth Bepi Colombo flyby by Mercury and the MERTIS data that we collected from the surface. So the MERTIS scientific goals are to create a global map of the surface mineralogy, to map the surface temperature and thermophysical properties, and using the data to investigate the permanently shadowed regions and to identify rock-forming minerals and surface composition of Mercury. Now, the instrument MERTIS that Harry as well explained in detail is on the slide, and MERTIS is composed of two parts. One is a spectrometer, it's called TIS, and the spectrometer is covering a range of 7 to 14 micron. And the second part is a radiometer, TIR, and that covers 7 to 40 micron. So what is very unique to MERTIS is the way we calibrate our instrument in orbit. We have two black bodies internal with 300 and 700 Kelvin, and we look into the, what was the laser? So anyway, can I go back somehow? Right, I can. And we look into the space, deep space as well, in order to have a temperature point of very cold. And this is what we do using the spaceport is pointed on the figure. So our, of course, looking at the planet in orbit, we're looking the planet port. Here, Mercury is also shown. And in order to observe the hot surface of Mercury, we have a very complex design of a baffle. And this baffle is designed to actually radiate away or reflect away any light that is coming in from out of the field of view. It is coated by gold, and it has these fins that are perfectly designed to, as I mentioned, reflect away the light that is out of the field of view. So as well, the design also allows to increase the thermal load. So at the tip of the baffle, when we observe Mercury, we reach the temperatures of about 100 Celsius. But as when we get to the instrument, the temperature is already dropping to less than 50 degrees. So, but yeah, as I mentioned, the planet baffle perfectly designed to look at Mercury. But what we did is during cruise, we had flybys by other planets. But the baffle is, the planet view is, of course, covered by the transform module. And therefore, we use the spaceport in order to do observations during flyby. So we observed the Moon, Venus, and Mercury using the spaceport, which was not designed, not planned, and not calibrated to do scientific observations. So this was really a big teamwork in order to make this happen. So as I mentioned, the spaceport is, of course, not designed to do scientific observation, and therefore we had to do post-launch calibration campaigns in our laboratory in order to understand the data that we collected. So there are, for the Moon and Venus flybys, there has been various campaigns, and they allowed us to very good understand the instrument. There are papers that you can read about, but then using this data set, using this analysis that we did, allowed us to actually preliminary calibrate the MERTIS flyby data. And we are, of course, now planning to improve this calibration. There are more tests to come. We are planning a test on the Bepi-Colombo spacecraft that is going to be executed in April this year in order to, again, do measurements using both ports and to characterize the spaceport better. As well, there is an experiment planned in the laboratory to do hot temperature measurements similar to temperatures that we observed from Mercury, and again, to better characterize these two ports. And here there is an image showing Jörn Helbert in the laboratory using a model of Mertis to do measurements. And of course, I could not have gone by this presentation not mentioning Jörn. As some of you might know, he has moved on to ESA to take on the role of head of solar system division, but he was leading the Mertis team for more than 20 years, I think. And I've had the honor of stepping up and replacing him at the DLR team, leading the Mertis activities there. So going back to the flyby, right, a flyby is always a unique geometry, unknown conditions. And here I dare to say we even looked at an unknown target. Mercury has never been looked at in hyperspectral mid-infrared data, so everything's unknown. And as Harry mentioned, the spaceport is actually located at the side of the radiator of the spacecraft. So here is again Mertis that you remember how it is, and I just turn it. So here the spaceport, you also see it in the right image with the red arrow, and we believe that there is some stray light coming into our field of view due to the fins. So that's what I'm trying to show with the yellow arrows. Yeah, it's about 1% of radiance of a spectrometer, so this shouldn't be a big deal, and we are working on characterizing it and hopefully very soon correct the data for it. But yeah. Yeah, here is again the radiometer data. We measured about 700 degrees, and the bumps that you see is due to the stray light. So let's have a look at the data. Here I'm showing you brightness temperature map, D-smooth, and this has been done by Mario Damor. If you want to know more about how the calculation has been done, stay in the session. This is the next talk. He's going to explain you all about it. But yeah, the goal here is to show you that we can see very nicely surface variations. We see different type of impact craters. We see different surface terrains. And this is, I think, a very, very nice data set to start working with. Of course, this brightness temperature is influenced by various surface parameters, including topography, grain size, temperature, composition, roughness, slope, shadow, albedo, everything's mixed here. And the next steps are to focus on each parameter and to understand what is playing a major role here. Right, so I would like to focus on the Basho crater and to show you a bit example of the surface variations that we can see in our data. So here you see the base map is the hillshade map based on the messenger DTM, and the color data are the brightness temperature. So blue is cold, of course, and red is warm. And the temperature variation that you see here from very warm to very cold is something about 10 Kelvin. So we see the Basho crater in the center shown by the, dark blue. And we see that as we go away, the temperature is rising. Here on the bottom, the blue profile is the topography profile, and the red one is the temperature variation. So the goal is that you can compare and see where is the crater, where is on the topography, and we can see also that the temperature variations are very nicely actually matching the crater, the ejecta blanket, and the surrounding area. So here is the MDIS enhanced color map. We see again the Basho in the center and the ejecta blanket very nicely. And now I'm putting the two color map images on top of each other. So here is the base map is the MDIS enhanced color, and the overlaid by the brightness temperature. So, and you see very nicely, I think, if I go back and I'll come back. So you see the Basho is, of course, shown by the blue color. We see very nicely the ejecta a bit brighter, and then and we see the surrounding area in red color. So it's nicely fitting the surface observation that we have. Right, so here is my conclusion. So the take-home message is that the MERTIS instrument is working very nicely and we are ready for the in-orbit operation. Scientific observations during cruise was not foreseen before the launch, but by reprogramming the instrument and being a bit thinking out of the box, we managed to do very nice observations during flyby. We have plans to improve the calibration of our data. And of course, there are plans to do more analysis on the data, to look at various type of terrain that has been already characterized, and also to focus on the mid-infrared range and to see what is new in this spectral range that has not been observed in the past. And I would like to invite you to, first of all, stay in the session. There are more MERTIS talks, and also don't forget the posters in the afternoon, and come to talk to us. We are at the poster session. Thank you.
Okay, thank you. Our next presentation is by Demore. Cross-instrument comparison of MERTIS and MASCS observations over Tolstoy Basin from Bepi Colombo's 5th Mercury flyby.
Okay, so I can start. Hi. So maybe my voice is lower than my normal, so if you don't understand me, just speak up. I try to be a little bit louder. So I will talk you about a little bit, okay, that it is. So the data I just seen before. So what we actually done was try to analyze the data and extract something meaningful to understand the surface, so the surface generally. So you see what it's about. So you already heard about MERTIS, and most of you in the room know already about MASS. The spectrometer was on board of Messenger, and the idea was to compare the two data sets to see if we see the same thing, we see it's different thing, or if the two instruments agree. The most important takeaway points here are the spectral range. So the channel of MERTIS that we're working with is 7 for 14 micron, and the spectral range of the this channel of mass that I was working with is from 300 to 101.5 micron. So that's completely different. But if you're looking at the same thing, they should have some correlation that we know from the lab. So we know the minerals, and we should be able to connect them. We're not going to this far, but you will see. So the region that I was focusing on is not the complete flyby data, but small region around Tolstoy Basin. And the idea was it's a really nice structure, big enough for our field of view resolution to resolve different structure. And we can see with both instruments, if we see correlation with surface geomorphology or different parameter that we can try to entangle with these two instruments. And why Tolstoy Basin? Because it's big enough and there's a really distinct differentiation between the interior of the basin. The outside is nice dark, so among the darkest on the planet. The structure is really old. I don't know, it's above 3 gigayears. And yeah, it's a lot of geomorphological structure that we hopefully see in the data. So this is the baseline of the data that I produced. The idea is here is really simple. I fitted the data, so each single spectrum, radiant spectra that we have, to a Planck curve and extracted the brightness temperature. So this gives us an indication of the surface temperature. And as you can see here, when we produce this map, we start to see that there are geomorphological features in this map, but it's not really clear because the absolute value is really high. So we are in the 700 something range as maximum, and the variation a few Kelvin on top. So as so much should before, sometimes it's 10, but it's really low. So what can we do to show this better? This actually. With a different approach and to not overdo things, what I did at the end was to smooth the data really well. So trying to get out the higher frequency variation and then normalize the data to this smooth one. What is staying here are the variation on top of this high temperature surface that you're seeing here. And here you can see how nicely the surface features are popping up. So you see even some annular feature, so you see lower temperature. This is actually variation of brightness temperature on top of the variation that you've seen before that's purely driven by mostly driven by the local time. So here, most of the local time variation should be taken off. And what we see here is related mostly to the surface we are looking at, sorry. Okay, just another couple of things that I was trying to check is how the geometry of the two datasets are corresponding or not. So in the central box, you see those are all the same area, and all these stripes are single observation from mass, from the visible channel, and the color on top is the local time. And in the box lower left, you see the actual local time versus phase angle for mass, and on the top, the one for Mertis. So Mertis, on the observation, got a really broad range of this local time, and mass was even brighter with lots of less observation, but the span was a little bit different. The red dots you see are just the Mertis data on the Tolstoy. And the far right, you see the two instruments. So the pixel are from Mertis, the rectangular one, and the other stripes are from masks. Okay, so on the top here, you have the brightness temperature. On the bottom on left, you have the brightness temperature without the smooth data, and you see that the surface, so the surface structure are popping out. In the center, you have the estimated temperature from this lower box from Mertis, sorry, attached on top of the Mertis. Sorry, I mixed up the two. On the other instrument, and you see that you see variation between the inside and the outside. On the far right, you see a plot about the reflectance at 750 nanometers from the mass instrument versus our dismuted temperature. And the bottom and the top plot, you see that the whole range of mass was not showing a real correlation. And I took out the data that have a different local time. So in the bottom plot, you see more or less the same local time. And you start to see at the beginning a slow trend. So it makes me a little bit more confident that we can actually see something. And here you see two cross section on the study area. Let's start from the left here. You see the brightness temperature, and then on top, this orange line is the smoothed version. And then the one I used to normalize this thing. So I subtracted, I took out all this trend due to the local time. And you see how this smoothed, it's showing a little bit better the variation. Then you have this, the third box is actually from the base map, and you see the crater in it. And then you have a local time plot. This small gap here is due to our calibration cycle in Mertis. When I create the big raster, there are lines missing, and then the rasterization process do some itch ups. And the top part is actually the same cross section over the longitude, so it's showing the same time. Just showing you that there are correlation between base map and the data. This is my final plot that you know, so you're already aware. The big takeaway message here is we have the study area with the camera image, enhanced camera image from Messenger here. And you see the interior and the outside part of the story, the glare formation popping out really well. So I enhanced the construct a little bit to show you it better. I show these three bands. So actually you have on the top and the bottom, this blue region are exactly on the Goya formation, more or less. And the center is just in the Tolstoy. From the left, you have the UV ratio, the visible ratio, and the 750 nanometer reflectance data from masks. And you see that you have in the Goya formation and the inside, you have a quite nice difference. Apart this peak in the south, that's exactly where this other crater is. So it disrupted the low reflectance material. So you see it's higher reflectance. The last box here is our temperature. And the big takeaway here is we see that in the center, we have higher temperature, and the Goya formation, both in the north and the south, we have a lower temperature, so brightness temperature variation. And it can tell us something about what we're looking at. The last plot that you see where the map is the actual the topography. And you see that the north part and the south part is a little bit higher. So a little bit is 2 kilometers, so it's high enough. And you have a flat part in the Tolstoy central region. And we're already at the conclusion. So the point here is, we have seen that the Tolstoy interior in our data, so in the both instrument, have a higher reflectance. So in relationship to the outside, it's pretty dark. And we have a high versus temperature variation. And we have a little bit higher, okay, that's wrong, actually. Okay, but the point is that we will possibly find a regulus. I try to interpret a little bit the data, so I may be wrong here because we, as so much show that there are a lot of interplay parameter here. So we are looking at surface variation, but it could be anything. But what I was saying is, could we possibly find a regolith for spread-rich material with different composition inside? In the north, so we've seen the two parts of the Goya formation resolved in my data. So in the north, we have lower reflectance, low BT variation, and dark color. And it could be related to possible space-weathered LRM or camera-rich material. In the South Goya, we have low reflectance, low BT variation, and dark color, as in the North Goya. What I think here is that the Goya North and the south show different VT variation. So if you've seen in the north, we have a lower temperature, and in the south it's low, but not that low as in the north. For me, this could point to a grain size difference, so a different thermal inertia, because from the enhanced map, you see that the color is more or less the same. So the composition should be similar, not the same, but could be similar. And this then, that's why I say that it points less to the compositional difference in the Goya formation. This could also be due to different implantation of the regolith after the formation of the crater, even it's really old. But because it's really old, we can have had gone through differential thermomechanical processing as well, due to the temperature of the surface. And also, as I said, in the south, yes, in this bright crater could have impact the size distribution of the regolith in this area. So impacting and then recreating a different distribution in the south part. So there are a lot of things that are playing role here. But it's interesting to see that the geomorphology is linked to what we see. And as a future study, we will do more things in this direction. My goal would be to have fully calibrated spectra, and then we can go back to the lab and we measure things that are similar, and we try to see if the two instruments could be matched using a single or different composition mineral or suite of minerals. That would be really interesting. And obviously with varying grain size and different things. As the other point out, we have a suite of different presentation, poster, anything. So if you want to know more about those things, just stay here or come to the poster session. We have a lot of different topics based on this data. So I'm already finished, 10 seconds before. So I thank you for your attention, and I'm letting you speaker. Thank you very much.
Thank you. And our final speaker in this first block of talks is Mattarelli, comparison of Mercury flyby data with PSL laboratory emissivity spectra of natural and synthetic samples.
So good morning, everybody. You probably heard that we had a flyby at Mercury. And you probably heard that we don't have the final calibrated data, so it would have been wonderful to present you the spectra and make some interpretation, but we are still working on the calibration, so it's in a very good shape, but we don't want to deliver conclusions too early. But so we thought about a nice exercise for this talk. So instead of Mercury, we took something that is very similar to Mercury. We had this big luck last year. Of a meteorite that was falling near Berlin. The name is Riebeck because it's the name of the location where it was falling down. And the very important part is that this meteorite it's not a meteorite from Mercury, so it's not a piece of Mercury, but it's forming in the same reduced conditions. And it's very rare to have a meteorite this kind. And you can see that, yeah. This is the search party, and this girl here, she will be giving the talk on Riebeck after the end of the first chunk. So a lot of pieces found, many grams, so it's a big fund, and typical size is a few centimeters, so it's quite an impressive sample. So what we did. We have this luck that in Berlin we have a strong collaboration with the Naturkunde Museum, so the Museum for Natural History Museum, and we have been using extensively the suite of instruments that we have there. So you may see the micro-CT, the X-ray fluorescence scanning electron microscope, and the electron microprobe at the museum. And this is a sketch of the lab. Already Harry was showing this, but the important part is the emissivity chamber that we use to measure samples under mercury conditions, so in vacuum at high temperatures. Again, back to Riebeck to give you some context. This is an elemental map of its mineralogy. So you don't see chondrules here, and it's quite a coarse-grained breccia, but it's surrounded by fine-grained matrix. So this is another small similarity to Mercury, the finer. And the very striking part of this meteorite is that the exotic sulfides, so alabandite, kylite, oldamite, and some minor metal inclusions. So no iron almost, and sulfides. So this reminds us of mercury. And the major components is enstatite and forsterite, and both are iron-free. And sulfides, it's more than 5%, so it's a perfect analog. So again, next talk will be extensively speaking on Riebeck. Just to give you an example, oldamite, it's the calcium sulfide and member, and you may see that there is some hints of of weathering and even the cracks inside. You may think you have to think that this meteorite was sitting on a moist surface for many days. There are some indication that maybe some parts of the meteorite were already weathered before we coming to Earth. And again, you see the enstatites part, and in this region you see a series of exotic sulfides, so iron and manganese sulfides, and we measure all of them in the lab because we have a collection of analogs, of synthetic analogs for the measurements. So just to give you an overview of PSL, of course, we can do many measurements. We have 3 spectrometers, and so we can do bidirectional reflectance in a very wide spectral range, and we can do hemispherical reflectance in another very wide spectral range, and micro spectroscopy, again, with the same spectrometer, so we can cover even high temperatures, so low to high temperatures, and of course the emissivity samples, as I was mentioning, that is this chamber is used to measure samples under mercury conditions, and of course we can do some more measurements that are not important for the planetary science, but for example, transmittance is being used to better quantify the optical parts of Mercury, so we can do our own calibration of the instruments at home. And just to give you an example, so different grain sizes, so from very fine to coarser. This is a study that we have been doing. So we create a mafic component that it's an orthositic plus glass, and then we started mixing calcium sulfide. So we choose calcium sulfide as one of representative for the sulfide. So we just started increasing the amount of calcium sulfide mixed, and this is only the Mertis wavelength range, just to show you that the effect is quite almost the same in the different grain sizes, so there is no dependency on the grain size, and you can see that in this region the effect is almost linear, so it's just shifting above by increasing the amount of calcium sulfide. It's a bright material, so you may imagine that the radiance, the reflections increases a bit, but here it's more you can see a higher degree of variation. So you already can see that in the spectral region that is covered by Mertis, we could see bigger difference due to the amount of the calcium sulfide. Just staying on the small grain size, so 0.50 for all the spectral ranges. We measured UV, visible, Vinier, and the MIR. Here there is a gap, so it's natural that this curve doesn't match this. It's not a calibration error, but you can see that we can provide those measurements for the whole suite of spectrometers on BepiColombo. And so we have the emissivity chamber, so we don't use the reflectance measurement, but we can go directly and measure calcium sulfide in vacuum at high temperatures. And this is this is a plot showing you 4 consecutive days of heating, because we wanted to see the effect of the thermal cycles on the sample. So you may see that the first day, for example, in this part of the spectrum, the lowest temperature measurement shows this peak still high as the other 2, so it's a nice triplet. But already increasing the temperature, you see that you have a difference here. No, sorry, it's a problem with the color. So just the 500 degrees and colorblind. I'm sorry. It's true, and so the highest temperature measurement just lift this peak here, and you can see that the following days this peak is staying there. This means you have been bringing some modification to the structure that stays. And again, this feature that it's quite triangular after a couple of iterations starts being rounded, and even this feature here, it's around 11 microns, got some modification due to the temperature. So as to say, this is just an example of what we can do in the lab, but it's important to have these measurements for the sulfides. And of course, we have been measuring all the sulfides that we have under these conditions. So we have a suite of measurements ready to be used for the interpretation of the flyby and of course, all the mission data. So I come to my conclusions. Of course, you know that it was the first hyperspectral measurements in the thermal infrared taken by Mertis on a Mercury surface. This is a new result. We are going on with the calibration. The detailed mineralogical analysis is in progress, so stay tuned. In the next months, we're probably gonna have a detailed analysis on this. We put our effort on Riebeck because it's a good analog for Mercury, and you could see the analogies are in the mineralogy here. The sulfide presence, of course, we can detect in reflectance just when few % is mixed to the mafic component, but in emissivity, the spectral features strike out. So next step will be to measure that mixtures in emissivity. And while we perfection the Mercury spectral calibration, of course, we continue measuring in the lab, and we are enhancing our spectral library for natural and synthetic and mixtures. And of course, the bidirectional measurements and the hemispherical too will be used for the broad spectral range instruments that complement Mertis on Bepicolombo. Thank you.
Thank you. I'm going to ask all of our speakers to please come up to the stage. And if anyone has questions, please come up to the microphones and state your name and affiliation.
Hannes Bernhardt, University of Maryland. So I understand that the global resolution of Mertis will be around 500 meters per pixel, but there will also be opportunities for targeted observations. What is the maximum resolution that we're going to have? How many % of the surface can we hope to cover with that? And will there be limitations where these observations will be, or can we theoretically target any place on the globe? That's to anyone.
So the goal is to have a global map, so covering the entire surface of Mercury. And for the targeted observations, we are actually currently discussing about that, but we cannot do all the time targeting. So there are special observation seasons in which we are planning to have targeted observations.
What will be the maximum resolution that you can hope to achieve with those? Ballpark.
I don't have it on top of my head.
I guess. I mean, okay, the what we declared in the mission was to have 500. I mean, it depends on the exact orbit and exact timing of those observations. Maybe you can go a little bit better than this, but don't expect to have meters resolution. So around the 500, maybe 400, but it depends on the exact orbit. We are doing the calculation almost now. So don't expect much better than this.
I was asking about the, do I understand correctly that there will also be, aside from the global data set, targeted observations of higher resolution?
I don't know if the resolution is going to be higher for because we are not going to go closer to the planet. We stay in the same orbit. It's just that we look at a specific feature on the surface.
Okay,
that's what I meant. So
yeah,
it could be a little bit better for the targeted, but not expect better than
I see.
But that's the point.
Okay, thank you.
Steve Parman, Brown University. Could you talk about the effects of space weathering on the spectra, whoever?
Okay.
Well, I think this is what we are working on right now. So all Mercury, the whole science is driven by space weathering, and we are working on it. But we're comparing with the lab. Of course, in the lab, we do lots of experiments and measurements, simulating the space weathering, and then we're comparing it with this Vertis data. And yeah, I can only say stay tuned and come back next year. I don't know if my colleagues have anything to add.
The only thing I can add, I remember from Messenger mission, you could see some effect on the space weathering. So we expect to see effects, but I'm not pretty sure. I mean, maybe my colleagues from the lab can say what we expect, but we need to work exactly in this direction. And the space weathering experiment is a bit more complicated for us. So we're on the thermal part.
I don't see you. One difficulty for the space weathering in the emissivity setup is that our cap is pretty large, so it's some centimeters, and we measure fine dust. So it's difficult to space weather that amount of material sitting in the cup that you have to use, because otherwise, if you have it and scoop the sample in the cup, then you lose the stratigraphy. This is something we have been thinking about since many years. A possibility would be to do this on a solid, on a pellet, and then scratch the pellet and have the thin layer. But this means many iterations of I don't know, laser or ion implantation. One part that we do routinely is the space weathering due to the thermal fatigue, so the heating. This is something that you saw already in the spectra. But yeah, it's a great point. I think in reflectance it's much easier. You just can deal with millimeter size samples, and we have here much larger.
Hi, Trevor Austin, Arizona State University. Very exciting new Mercury data. Can you please help me understand the linear artifacts in the Mertis image, both the north and south ones and the sort of diagonal ones? Not a complaint, of course, because it's exciting in any event. And I was wondering, during orbital operations with repeated observations, like how well we're going to be able to work those artifacts out.
Okay, good point that you noticed this. And okay, there are two different things. So the diagonal strap that you've seen, those are due to our calibration cycles. It means that we look routinely to internal black body to check if the calibration are good and to actually have a reference point for this thermal environment that the instrument is in. So it's, I guess it was, I don't remember exactly, we changed a couple of times, but it means that after a fixed setup of observation at the 20 or 100, you look inside, and then because the spectrum is moving, then you have missing strap on the surface. That's are the diagonal. The other strap, there are pixel-to-pixel variation that are linked to what Solmas was showing. This part view was never fully intended to do observation. Those are remaining effects. And if you've seen, those are on specific pixels. So specific pixel has a little bit higher radiant signal than the other. And those are completely artificial. So you see this longitudinal feature those are fake, let's say. So there's remaining of the calibration, exactly what we're working on now. Yeah, thank you.
I will just put a quick note to those who are on Zoom to enter your questions in the Q&A, and anyone else in the room if you have questions. Until that time, I will go ahead and use Chair's prerogative and ask a question about, and bear with me as I'm still trying to wrap my head around these data, but the relative, I guess the question would be about the relative influence of grain size in your eventual spectral determinations, particularly for features that might be below your nominal spatial resolution. So thinking about Tolstoy, where you're showing this difference in the Goya formation, there are a number of pyroclastic deposits in and around that area. So I guess I'm wondering, what are the relative effects, and can we use grain size or these variations in grain size to sense features that might be below the spectral resolution, or is that too subtle of an effect?
That's for me, I think, no? Thank you. Okay, that's a good point. I didn't show I showed the map really quickly, but inside in TOSO, we have a good resolution for the flyby. So in orbit, we're gonna have much higher resolution. So it depends on the progressive structure you're talking about, how big it is. I think it's a really good point. If we do laboratory model, we can have, I think, a pretty strong effect on the grain sites that we can see sub-pixel. So I think it's something we can afford to see.
I can add something. In Berlin, September 24, we had a Mercury laboratory workshop. It was the first one, and there were people from laboratories all over the world, but even scientists that use laboratory data. And we have been defining some working groups. One working group is the sample characterization, and I am co-leading the working group, and we have some posters. So, for example, if you come to the poster session, you will see an extensive study on grain sizes, really dividing the grain size into smaller and smaller and smaller ranges. And it's a very long study because it foreseen 2 N members, 15 grain sizes for each. So it's 30 plus you start mixing. And so would be hundreds of measurements, but then together with some modeling, we aim to have a pretty good description of the grain side effect on the spectra.
That's very exciting.
Hi, I'm Emily Lakdawala, freelance writer writing for Sky and Telescope. Congratulations on getting Mercury light on your detector. It's very exciting, especially because it's a lot earlier than expected. I'm wondering if you're having any plans to release perhaps a snapshot or something just to show off to everybody how great the data look. It does look fantastic. So congrats on that.
Emily, thank you for the question. Of course, we are more than happy to share the data and not just a snapshot. You know, once we have the data calibrated, or we think we have a decent calibration, then we will share very happily. I mean, we are not trying to hold back anything. And yeah, if you need a snapshot for public outreach or whatever, please talk to us and we send you whatever you want. Okay.
How long do you expect the calibration to take?
Oh, that's the tough question. You know, we don't know really, but you know, there are some spectrometers that were on space missions that took years to calibrate. Now I'm hoping that we are a little faster, you know, but we're trying to, yeah, Mario just said this year. So we have a colleague at DLR that's looking into the calibration. We have a second instrument actually at DLR that allows us to use the instrument and do all the measurements that are necessary. So yeah, we are hoping that we are coming up with a halfway decent calibration by the end of the year. Okay, but for the snapshot, we are happy to send you whatever you want.
Just if I can add just one thing, I'm also the acting archiver for the data. So the archive structure is pretty solid. So it means that as soon as we get the data, I'm updating everything to the last PDS version, everything. So the box of the data is already there. So we just need to have the final thing and to be pretty sure to deliver something that is, we are 100% sure that it's true. So as soon as it's ready, we're out. No? Yeah. It's good. Oh.
So as we have time, I can ask a more hypothetical question. Alice Berg at the University of Maryland. So I'm interested in cold spots on the moon. And these are features that if they exist on Mercury, or corresponding a feature exists on Mercury for young craters, it will be pushing your resolution limit. But if we take the largest ones that we see on the moon, they should be resolvable with Mertis. Do you, if they're there on Mercury, do you foresee any specific issues that Mertis might not be able to see them if large enough ones are there? Or would you say, like, yeah, if they are there and large enough, like the largest ones on the moon, we foresee no issue that Mertis should not be able to see them?
You mean the permanently shadowed craters, for example?
No, I mean the cold spots that surround young craters on the moon, which we're still discussing how they form, and we have a few good ideas. So if you would see them on Mercury too, that would really limit the potential formation mechanisms. but they are just 2 to 3 Kelvin, sometimes colder than the surroundings. So the thermal resolution is also important. But as I said, the spatial resolution in terms of the largest ones we see on the moon should be resolvable by Mertis theoretically. And I would like to hear your ideas on that.
Are the structure that you're talking about? So how big is in the moon? I'm really not the moon person.
So they can have diameters of hundreds of kilometers, but they have those filaments that range out. So you probably won't be resolving the finer structures within them, but you should, for example, if you see a very young crater like potentially yesterday crater, the youngest craters within a certain size range, and you see like a colder area around them. You see a warmer area right where the crater is due to the higher block density and all that, and then it's surrounded by a colder moat. That would be a telltale that we potentially look at something like a lunar-style cold spot, which is probably a regolith effect. But do you think a few Kelvin is something that would be resolvable, also pushing the spatial resolution? But as I said, a few hundred kilometers, they could be that large theoretically.
On the technical operational side, I think it's doable, and even due to the temperature resolution, it's doable in our range. And I mean, the spatial resolution, if you talk about 100 kilometers, for sure, something we can see, but the final structure, I think it's something we can do. And even with repeated observation, so lowering the noise, so I think it's something that we could resolve.
The radiometer resolution is below 1K, so we will get it for sure.
If they are there, we'll tell you.
Yeah, exactly. That would be very interesting to look at.
Okay, thank you. Thank you. That's very interesting.
So I have a question about calibration, which is what we've been talking about today. And as you guys have mentioned, these are fortuitous observations. They were not planned. They were not thought that they were going to be happening. So all of this calibration effort has been for a system that you never really thought you were going to be using. My question is, how will what you've learned from actually getting Mercury data in through your instrument in this calibration process, how will that influence your actual calibration with your planned observations once you get into orbit?
Well, it allows us to much better understand the data. So we really understand what is it that we detect, what are the limits, and what to do with them as well. And I think I mean for sure we learn a lot also for the calibration once we are at orbit, but what we can learn from it we cannot yet say because we haven't learned it yet. So it's in the near future.
The main point I think is we learn we characterize the instrument well better than before. And second thing, we characterize it in space. So we did, as Shramat showed, to different targets, and each different target, the Moon, Venus, and Mercury, had different characteristics that we're looking at. And it means that we have to understand how the instrument behaves looking at this target. And for Moon and Venus, we was never planned to observe those cold things relative to Mercury. So we learned a lot about how the instruments behave in this lower range. So we can do things like colder observation, other things a little bit better now, more confident than previously.
The difficulty is that all the target body that we observed, so the Moon, 2 times Venus, and then Mercury, they were in extreme conditions, so often very far away, and then we don't have a statistic. We haven't measured this for 2-3 times, so it's just one shot, sometimes with an inertial orientation, so it's a little bit complicated. But we are working on this, and we use the checkouts that we have regularly, even to improve the knowledge on the detector, on the performances. But it's just that it's missing the good known target that you use to improve your calibration, because every time is a new target, and it doesn't come again in the same form.
Okay, our last question in the room.
Alex Sankey, Arizona State University. General question about the instrument. I believe I read that the black bodies are graphite in composition. Is that correct?
No, the graphite is the black body for calibration in the lab. But on the instruments, the black body are well, it's 2 black body. One is an extreme hot source that mirrors in a mirror, because of course in an instrument that is sensitive to temperature, building a 700K black body means you're heating everything. So this was a way to keep the instrument temperature low, but to have a relative high emitter. And the BB300, so it's at instrument temperature, at room temperature, I would say. This is a standard black body covered with Acta paint.
Okay, so then using the graphite black body in the lab, does that present any issues for trying to detect a graphite? I mean, I'm assuming maybe it's featureless across the range of the instrument.
Graphite is featureless across the whole spectral range. So the only way you can detect graphite is just presuming that you don't have it and then seeing the difference. So we have some studies on this. So we had an EC group that it's working on many aspects. One of these is adding graphite. There is another poster at the poster session that shows a little bit this.
Thank you.
Okay, let's thank our speakers again. Okay, we're going to move along to our next talk by Vanda Neuken, Mercury's Surface as Seen by MERTIS, Early Insights from Laboratory Analysis on FeO-Free Materials in Comparison to Bepi-Colombo MSB number 5 data.
Hello, everybody. My name is Aurélie van den Neuker. I'm a PhD candidate at DLR Berlin. And just like my colleagues before, I will also be talking about our MERTIS flyby-5, but more on a focus on lab measurements with the FeO-free mercury analogs. So I'm sure most of you are familiar with Mercury surface, but for the people who don't know, past mission Messenger revealed us that the surface of Mercury is composed of mostly a low bulk iron, titanium, high sulfur carbon contents. And the most important for my talk in this case, since I want to talk about iron oxide-free samples, is that there was no absorption bands related to iron oxide-free detected in the mafic minerals. Mafic minerals, I'll talk about instatites and phosphorites, and this is something that we knew from Messenger and that we would also expect on the new data that was collected by MERTIS now with the flyby-5. So now, which analogs did we choose for this study? I think, thank you for Alessandro that introduced my talk. We were very lucky to have a mercury analog that fell near Berlin in a small town at Rebeck, which was a very good analog because it contains a lot of iron oxide-free minerals. As you can see here on my screen, we have one of the Rebeck obrites that was actually collected by our team, and next to it an XRF image. You can see that it's mostly blue, and this is because it contains a lot of silicate materials. We, of course, made more precise measurements with a microprobe that is depicted here in this table. And in the blue box, you can see the iron oxide contents. And I can tell you that we had iron oxide in very small quantities. It was below our detection limits. So this means that this, if you want to look at iron oxide-free spectra to compare to MERTIS data, this is a very excellent analog. And the reason why this is very similar to what we expect on Mercury is because it has been formed in similar reduced conditions as on Mercury. So it doesn't mean that it comes from Mercury. It just means that it was in the same anoxic environment formed and also in a very reduced way. Of course, it's a rock. So a rock, it might be hard to compare surface data to a rock sample because it's composed of different end members. And that's why we chose a wide variety of mineral end members that we also expected on the obrites, but that are very distinguished and made in laboratory facilities that can actually make this iron oxide-free end members. And I would like to thank Olivier Namur and Bernard Charlier that helped us with this study because they did a lot of work on this to make these samples iron oxide-free. As in nature, we can find them a lot, so phosphorite and andesite, but they always have certain % of iron. So in this study, I will be talking about andesite, phosphorite, plagioclase, microclean, but we also had a lot more measurements that were not covered in this talk, but maybe in the future I will. I will not talk. This is our lab facility that was also introduced by Alessandro before, but I want to show it again because what's more in this picture is that I show our crushed down Rebec oberite here on the left-hand side. You can see that it's pretty coarse grains. It's more than 50 microns than what we expect on the regolith. However, the reason why is because we wanted to do some micro FTR measurements on it. So if you have full grains, then you can do better characteristics on it. But no fear, we also crushed down our sample even more to 50 microns and also all the end members to have the same regolith material that we expect on Mercury. Of course, I talk about Mertis. So we use emissivity to do our comparisons. So we heat up our sample up to 450 degrees, which is the surface temperature of Mercury. And then we get emissivity spectra that we can later compare to remote sensing data. Again, why do we want non-terrestrial samples? Well, this is the proof. So this is reflectance spectra. And in the dotted line, you can see the terrestrial sample. So it has a lot. This is phosphorite, by the way. You see a lot of absorption features here that, for example, are not seen in our synthetic end member. And we have the same with enstatite. Even if it's more reduced, we still see absorption features that appear and disappear depending if you take an iron oxide free or one with iron oxide. So it's very important that we have these samples to do our comparisons. But of course, you're all here for emissivity spectra. So now I'm going to show you this. Like I mentioned before, I measured 4 samples right now that I will show in this talk, and they actually show all the same trends. So I will just go over them and explain you what the most important parts are here. So here we have anorthite on the left, microclean on the right. And how it looks like is that we measured our sample from 250 degrees up to 450 with a stepwise of 50 degrees with the blue line on top. Okay, the laser doesn't work, but oh yeah. The blue line here is the lowest temperature, 250, and the highest temperature, 450, is lower. So we actually see a spectral darkening by heating up our sample. This is expected, nothing new. However, what we are very interested in is a crystal feature that is here depicted in the light gray box. And we see actually that our crystal feature position moves with a higher temperature. And this shift is very important because if we want to compare our crystalline feature from our lab with the crystalline feature that we measure with orbital data, we need to take into account that temperature plays a big role. So the shift is with a high temperature towards lower wavelength range. And we see this with these two, but we also see it with the next two. And this is phosphorite and enstatite. And now I want you to have a look at the enstatite on the right. Just remember a little bit the shape of it. And well, this is our Rebec oberite. And if you remember a little bit the shape, it's pretty similar. And this is good news because with XRF data, we saw that, we remember the blue XRF image. It was mostly composed of enstatites. And this we can also see in our spectra. So the dominant spectral features are dominated by enstatite. This corresponds. So this is very nice. Of course, we have some differences. For example, in the beginning, this might be because of the phosphorites, but more about this in the next talks in the future, hopefully. So now, let's talk about Mertis. Of course, I'm not going to show more than what was explained in our previous group. However, I want to go more into details about one location. So this is, again, our estimated brightness temperature map that was shown by Salmas before and our team. However, please take note that colors are inverted. So the blue part is the hot part and the red is the cold part. And you see actually temperature variations here, of course, expected. But now we want to look more into details in the Tolstoy region, for example. And if we look at the estimated brightness temperature here, we also see that even on a localized area with a local time that remains around 1 p.m., we have variations in our temperature. Being here 700K in the blue part, going here in this site with 720K. So these variations here are important because remember when I was talking about the changes of the crystalline feature position with temperature, even if we expect to have, so Tolstoy, for the people who don't know, it's an LRM. Even if we expect to have similar mineralogy here, there still could be a change in the crystalline feature position depending on the surface temperature. So that's why I want to really highlight this here. So please take in mind Crystal features should also be seen in the orbital data and taken into account. So this shift is something that we need to look into. Now I'm at almost the end of my presentation, but the summary here is that I want to say that we measured a wide range of iron oxide-free samples going from the natural Rebec obrites going to the end members. This is a study that is still ongoing. We will continue with more samples on this and also after mix them. As you saw with the obrite, it is a rock. We had the enstatite that was dominant there, but we don't know. Could it be that the enstatite is dominant even in 10%, 20%, 30%? This is something that we need to investigate, and that's why we will do also mixtures with these iron oxide-free end members to see, okay, at what point will it be dominant in the spectra? Yes. And also the major point is, of course, this crystalline feature shift that we see with a higher temperature. So the main goal of our study is actually to see spectral similarities and differences between our lab data and MERTIS data from BP Colombo, also with orbit insertion, but also with our flyby, and also future data like symbiosis, because we measured the reflectance. So this is also something that can be done, and past data from messenger like masked data. And of course, ultimately, what we would like to know is what's the surface of Mercury composed of course, but this is a very long shot. And I think we are with a big team to work on this, so yes. And please have a look at all of our posters. We are not doing this alone. So thank you very much for your attention and see you soon. Thank you.
Okay, for the next talk, we have a change in speakers. So we have Jeff Gillis-Davis taking over, and the title of the talk is An Experimental Investigation into Carbon as a Space Weathering Product on Mercury and Carbonaceous Asteroids. Jeff, all yours.
Good morning. It's my pleasure today to show you our results from a three-pronged approach to studying how carbon may be responsible for at least some of the darkening on Mercury. You get me instead of Autumn or Carrie because they're both off taking ITRF data in Mauna Kea of some asteroids. So despite Mercury having a very low iron abundance in its regolith, it is dark. Its albedo, roughly around 10%, is closer to the lunar maria than it is to the lunar highlands. Carbon's been hypothesized to be present, and the darkening agent creating the surface darkening, just like we see for carbonaceous asteroids. And the concentration of carbon might be up to as high as 5 weight % in some areas, and can be similar to C-type asteroids. What we don't know is how this carbon being present in the regolith, what form it is, and if it can be utilized like iron to make either nanophase carbon or microphase carbon in space weathering products. So that was the aim of our experiments. We simulated micrometeorite bombardment using a laser, and I'll get into methods on that, and using some regolith analogs. We started off with San Carlos olivine, which has about 9.5 weight % iron, and you can see it creates this really big 1 micron absorption. To be more similar to what we think Mercury's crust might look like, we used the phosphorite and enstatite, which were iron-free, and their spectra plot up here. You can see with the lack of iron, there is no 1 micron absorption. We then mix these silicates with 5% carbon-bearing opaques. We use 3 different opaques because, again, we don't know what might be the carbon phase on Mercury's surface. So we have a graphite with its more ordered crystallinity, has its own spectral feature. Anthracitic coal, still kind of red, different spectral feature in the UV. And then carbon black, which is amorphous and has really a blue spectral curve. And you can see here we're going just from 8% to about 0.1% reflectance. So everything here is way down here. We focused first on San Carlos olivine because it is a common mineral used in laser and ion weathering experiments. It allowed us to have confidence that the methods that we apply to our phosphorite and enstatite carbon mixtures is also reproducible. This is the space weathering lab I have at WashU. What you're looking at right here is the restrictor funnel. The powders we use are not compressed, they're not solid. So when the laser hits it, it stirs it, it gardens it. If we didn't have a way to contain it, it would be all over the floor of the chamber. We use a 1064 laser. We use a short pulse laser that creates vapor, which is the canonical way of doing it. But we've added in a second laser that has 10 times longer pulse width, and that creates a melt. And this allows us to make agglutinates like you'd find on the moon and what we would suppose would be on Mercury. We do about 20 shots per second under vacuum of 10 to the minus 7 to 10 to the minus 8 torr, and we are able to make agglutinates and weathering products. You can see this is the starting material of a San Carlos olivine, and this is after 32 minutes of weathering with the laser. So the results, we are able to, the spectral results, we're able to see spectral reddening. We see a decrease in reflectance and near complete removal of the 1 micron feature for olivine, which is again is something that you don't see when you only use a short pulse laser. And we see a change in the curvature of the 300 to 700 nanometer region for the enstatite mixtures. So this is San Carlos olivine fresh, and then after irradiating it for 32 minutes, we call this mature. Kind of like on the moon or after 1 billion years, you don't really get much spectral change if you just keep blasting with the laser. So we think this is equivalent to about 1 billion years of weathering. Here's our enstatite example. Again, this is the fresh spectrum. This red spectrum is just a comparison to a Klima pyroxene that had a little bit, just 0.06 weight percent iron. As you can see, even that little bit of iron goes a long way. When we weather our just pure enstatite, no carbon in it, we see it does darken, creates a nice reddening slope. These spectral features here, which are probably due to water, are also lost. No big surprise. When we take our fresh enstatite and mix it with our 3 carbon phasers, you can see this is 0.3 reflectance, so we're way down here on this plot. You can't even see it compared to the weathered material. So this is fresh enstatite mixed with our 3 carbon phases. You can still see they have unique spectral features due to the different carbon opaques. This is the same plot as before that was on the right. Now this is after weathering. We have enstatite with just a short pulse laser. So this is, we just hit it with the short pulse only, that's 6 to 7 nanoseconds. When we do the dual laser weathering, it gets a little bit darker. But you can see that the enstatite plus coal is still different than the enstatite plus graphite, which has a less roll-off in the UV and is much darker. And then the enstatite plus carbon black is just a flat line and very dark. Now, when we look at the features on the surface, we can see there is lots of melt. This is San Carlos olivine, substantial melt. We can see some nanophase iron in the TEM sections. We see the same things in the enstatite. We also think we have graphitized some of the carbon black. This strip right here is where we put carbon down as a strap to protect the material, and the lift out that you'll see in the next slides came out from here, the TEM lamellae. So this is the TEM bright field image. All of this is the carbon that gets put on the top in a gold layer to disperse electrons. Things that are high Z are dark in this feature. So the nanophase iron that we created is dark in this big, thick amorphous room, which is over a micron. And we have 2 different size populations, kind of a larger size and a very fine grain size. And then we have some recrystallized damage region, which could be created by either the laser hitting it or the olivine being recrystallized in the hot melt. We also see some vesicles. So these weren't even ion irradiated materials, yet we can create vesicles. Now we're switching over the enstatite and carbon black TEM section. We noticed in SEM images and the TEM, the enstatite is actually polycrystalline, so it's very small inclusions. And in the TEM section, again, here we see some dark areas This is the HADF image. And we thought these might be nanophase inclusions of carbon, but when we re-thinned the thin section and looked at it, we noticed it was actually just vesicles. So we haven't actually found any nanophase iron or nanophase carbon in these features, but something is going on to definitely darken it. We also see that this is some carbon black on top. You can see on the TEM image that we actually get some twinning in here, and we think that's showing that we've gone from an amorphous carbon black to a more graphitic carbon. And in the image down here, you can see the size of the polycrystalline enstatite crystals. So the extent of weathering, we clearly see physical changes, as I showed you in the SEM images and the TEM and visual darkening. We clearly see spectral changes for these high to very low iron materials, darkening, and slopes very similar to the VNIR data with the roll-off for the dark planes. And we also see that the choice of the analog material matters, whether we're using the graphitic carbon or the carbon black, and having the iron-free synthesis is behaving like real minerals spectrally and physically. They don't melt quite as efficiently as the San Carlos olivine, and that's because they don't have that 1 micron absorption where the laser is focused. But we are confident that the method is working. We see from the San Carlos olivine experiments, it works as we expected, and it continues with the enstatite and carbon black. We will be looking at these features in thermal infrared emissivity next, but we have taken some mid-IR spectra, and they look very similar to Kremer and Hamilton mid-IR for olivine and enstatite. So we think this might be a good explanation for why mercury is so dark, yet very low iron. The carbon is, when you weather it, not when you just look at it when it's fresh, darkening and reddening the spectral slope, looking very similar to the low reflectance material. And the physical alteration is what you would expect for space weathered materials. We still try to find whether the nanophase carbon might be going into these materials and creating the darkening. So it's something we're still looking at, hopefully with some more TEM work. I think that's all I have time for. Thanks.
Our next speaker is Isaac Narrett, and the title of the presentation is, Does Mercury's ancient crustal magnetization require a stronger dynamo?
Hello, so I'm Isaac. I'm a graduate student at MIT, and today I'll be talking about Mercury's ancient crustal magnetization. So currently Mercury's generated magnetic field is anomalously weak by orders of magnitude based on conventional scaling, both from arguments of energetics as well as the dynamo region size. And so we want to know how this dynamo might have evolved in time. Specifically, would the past dynamo maybe better follow these conventional scaling laws? And so we will use some surface properties to maybe be able to tell how this dynamo has evolved in time. So currently Mercury has about a 200 nanotesla dipole field measured at its surface, and measurements from the MESSENGER mission measured very strong crustal fields, about 10 to 20 nanotesla at 20 to 30 kilometers altitude, which have been inferred to be sourced from ancient thermoremnant magnetization from a poorly constrained ancient field anywhere from the current field strength all the way to an Earth-sized field of 50 microtesla. And so the idea is that surface material that was heated would cool in the presence of this background field and record a magnetization as the process cools. And so we want to ask, what exactly was the source field when this ancient magnetization was set, so we can learn more about how the dynamo field has evolved in time. And so there are two main suspects for the magnetic fields that would have been present during this ancient period. One is the interplanetary magnetic field, which is sourced from the sun as the streaming solar wind flows throughout the solar system. And the other is the Mercury dipole field sourced from Mercury's interior. And so we need to know which of these fields would have been dominant at the surface to know which would have sourced this ancient magnetization. So one way we can do this is by looking at how a magnetosphere forms for a planetary dipole field. And so this nominally comes from the balance between the streaming solar wind dynamic pressure and the magnetic pressure from the planetary field. And the location of this pressure balance can set where this process occurs, which is called the magnetopause. And so for a sufficiently strong planetary field, you can have a magnetopause that is above the surface or well above the surface. And as this magnetopause distance is located further from the surface, you're more and more dominated by your steady internally generated dipole field. Where conversely, if you have an extremely strong solar wind dynamic forcing, then your planetary field might not be able to stand off the ancient solar wind, and thus you won't have a magnetopause that is above the surface. So you'll be subject to any IMF variability or magnetospheric field variability at the surface if this is the scenario. So how does this affect surface magnetization? So nominally, material that is cooling in the presence of a background field can record the external field via the alignment of the dipoles within the material, and this will form a uniform magnetization if the background field is steady over this cooling time. But if we have a non-steady field like the IMF, which has directional and magnitude variability over the cooling timescales, this will result in a misalignment of the internal dipole moments, and you'll have a net weaker magnetization. So we'll say that non-steady fields are fields that vary over these long cooling timescales. And so to be a little bit more quantitative with this, on the x-axis, I'll plot the cooling layer scale length, and on the y-axis will be the time scale. And so from theoretical conductive cooling times, we see that large magnetic layers that are cooling, like a 10-kilometer thick layer, can take millions of years to cool. So this means that any magnetic field must vary on timescales shorter, or any magnetic field that varies on timescale shorter than this conductive cooling will result in a non-steady TRM, whereas any magnetic fields that have longer variations will be able to record this steady uniform magnetization. And so plotting the IMF variability as well as the rotation period, which can affect the magnetospheric fields, you'll have non-steady fields in the presence of these large cooling layers, which will result in a non-steady TRM if you have the IMF dominant at the surface. So to be more quantitative with the magnetic field environment at Mercury's surface, we'll first assume that we have the current weak modern dipole field. And on the x-axis, I'll plot the solar wind dynamic pressure range, and the y-axis will be the calculated magnetopause standoff distance. Whereas you move up on the y-axis, you'll have a larger magnetopause standoff distance, meaning by proxy, you'll be more dipole dominated at the surface as you move up on this plot. And as you move towards the bottom, you'll be subject to those short time scale IMF variabilities or magnetospheric fields, which can affect surface magnetization. And so there's a wide range of inferred ancient solar wind dynamic pressure range for the young active sun, which is, as you can see from the reference yellow star, is much, much larger potentially than the current Mercury conditions on average. And so based on this transition region where we change from the magnetic field source, we can then plot how our current dipole field at Mercury would scale in this parameter range. And thus we see that the modern Mercury dynamo is not strong enough to stand off the ancient solar wind, and thus you'll be subject to any IMF variability at the surface. So in order to show how this would fare with magnetizing the surface, if we had this variable IMF, we use ACE spacecraft data scaled to ancient Mercury conditions and use the thermal cooling and magnetization model from Sarah Steele's 2024 Mars paper to show how a magnetized layer would form in the presence of a variable IMF. And so as this large layer, typical for Mercury crustal field sizes, cools through its Curie temperature in the presence of this variable IMF, we find that we get 1,000 times weaker crustal field generated from this variable IMF relative to what would be formed if the same magnitude IMF was steady over this long cooling time, assuming the same volume of magnetized material as well as the magnetic mineralogy of the volume which is given by chi-TRM, or the efficiency of the material to record a TRM. So that brings us back to this plot where we want to ask, how strong must the dynamo have been in order to stand off the solar wind and be dipolar at the surface, thus be steady over these long cooling times? And so from this, we can show that a 10 times stronger dipole field would meet this requirement and be able to stand off the ancient solar wind for the large range of solar wind dynamic pressures in the ancient Mercury environment. And so then we ask, what is the allowable parameter space to create these crustal fields that MESSENGER has measured today, given a 10 times stronger dipole field in the past? So on the x-axis, I'm plotting the magnetized layer thickness, and the y-axis is the efficiency of the material to record a thermoremnant magnetization. And any colored in region on the plot will represent parameter space allowable to produce these crustal fields measured by the MESSENGER mission. And so I'm showing here some typical parameters for Mercury surface conditions. This chi-TRM range is poorly constrained based on uncertainties in the Mercury mineralogy. And on the vertical plane, we have this average crustal thickness to give a sense of how large these layers might be. And so we can see that from this plot, there's a large parameter space that can create these very strong crustal fields that have been measured today. And thus we see that the dipole field, if it was 10 times stronger, is both able to stand off the solar wind and will thus be likely over these long cooling time scales. So in summary, I've shown that the modern Mercury dynamo field was not strong enough to stand off this extreme ancient solar wind. And thus, if this were the correct scenario, the variable IMF that would be present at the surface would not be strong enough to explain the Mercury crustal fields measured today. And so the ancient dynamo field must have been stronger, maybe 10 times stronger, in order to be able to stand off the solar wind and have its dipole field be steady at the surface in order to magnetize the crustal fields that are measured today. And so to leave you with some concluding thoughts, if we change the ancient dynamo magnitude for these conditions, we can then ask the question of what the interior composition or the interior structure might have been different in the past conditions, which can hopefully inform future dynamo modeling of Mercury's interior. Thank you.
Thank you. I'm looking for the next speaker. It's already up there. Sorry, missed you. So the next presentation is given by Gigetti and Johnson. Title is Magnetic Signatures of Craters in Mercury's Intercrater and Smooth Plains Units.
Good morning, everyone. My name is Filippo. I'm a PhD student at the University of British Columbia in Vancouver with Catherine Johnson. And we are studying the crustal magnetization of Mercury. Today, I'm going to present some of the results of our study on craters, their magnetic signatures, specifically with a focus on the difference in crater magnetization between the two geographic units, smooth plains and intercrater plains. So this is our starting point. It's a magnetization thickness product model in a stereographic projection. This is the northern hemisphere of Mercury. More about this model later today in the poster session. What we're interested in here are signals associated with crater interiors. And you can see here two clear examples, Biasa and Rustavelli. In most cases, obviously, if there's any signal, it's more subtle than this. But the reason why we're interested in this crater width signal is because we may want to look for relative timing of magnetization. By using these craters, their relative ages, and the information on whether their signal can be induced in the modern day field or maybe ancient, so remnant or ancient. Obviously, craters, the lack of magnetization can also help towards building a dynamo history. Or we can use these craters for information on lateral variations in magnetic carriers, and whether these are intrinsic or, as we will explore further thanks to impact delivered iron. So if we zoom in on Vyaza, there's the light. Vyaza, we see this nice crater with all the magnetization thickness profile lines that you can see in this panel in the bottom. The solid black line is the average magnetization profile, which is clearly associated with the interior of the crater, delimited by the vertical lines. And additionally, you can see this dashed black line. That's the maximum magnetization thickness product that can be induced in the current field of the planet at Vyaza's location. And you can see that the signal associated with the interior of Vyaza is higher than that. Anything that's above this line is possibly remnant. We have several craters with this same situation. So our goal was eventually to map craters in the Northern Hemisphere and to quantify their magnetization signature or lack thereof. And to do so, we use this quantity that we call the magnetization ratio, which is simply the ratio of the average magnetization thickness inside the crater to that outside the crater. We further defined the crater to have an enhanced magnetization if its ratio is larger than 1 at the 1 sigma level at least, and similarly to have a deficit if its ratio is smaller than 1. And you can see results here in this map, which now is a Mercator projection of the Northern Hemisphere with deficits and enhancements plotted. As I was saying, if we're interested in relative timing of magnetization, what we want to do is to link deficits or enhancements to the relative age of craters. So we end up with these degradation class histograms that look like these, from which we can, however, see that enhancements or deficits are not related to any specific degradation class index or group, degraded versus fresh craters or buried. So from these results, we cannot really say much about relative timing of magnetization. But we further explored an interesting subset of these craters that you can see here now. This is the same map with the same craters. In white, you have all the craters whose magnetization can be induced in the current field. These craters with a green outline are basically the enhancements from the previous slides. And now the darker green craters are the craters part of the subset that we're analyzing. So craters with an enhancement, more magnetized than their surroundings, and whose magnetization is too strong to be induced in the present field, which means that it possibly remnant. But if we look at the degradation class histogram for these craters as well, you can see the dark green bins. Again, craters span all degradation classes, and we don't really have any indication of relative timing of magnetization. At this point, we may be interested in looking for an alternative explanation for these enhanced magnetizations, especially, and we are thinking of impact-delivered iron. And part of the reason why we're thinking about this stems from the difference in number of enhancements and deficits between the two units, as I was mentioning at the beginning. So if we look at the intercrater planes first, we can see that most of the craters have a magnetization deficit. And out of all the craters with a deficit that we cataloged in the study, 59% of them, so many, are found in the intercrater planes, as opposed to only 27% of enhancements that are found in this specific unit. If we go to the smooth planes, the situation is reversed. We can see most of the craters that have an enhancement in this unit. And out of all the craters with an enhancement that we cataloged, 56% of them are found in the smooth planes, as opposed to 27% of deficits found in this unit only. So at this point, the question would be, what makes the smooth planes special? Why is it that we see more craters with an enhancement in the smooth planes? And we believe that additional impact-delivered iron may answer this question, especially when we consider the difference in iron content between the two units, with the smooth planes having a lower weight % iron compared to the intercrater planes. So let's now assume that we have an impact that can deliver iron, enough iron such that a magnetization enhancement can be detected. So if the impact happens on an ICP, intercrater plane terrain, we will have additional iron, which will create a lateral contrast in iron content with the surrounding ICP terrain. This contrast will be a magnetization enhancement detected. And we have 17% of craters in the intercrater planes that are an enhancement that can be explained like this. In the smooth planes, the story is a little different because we have different scenarios possible. If we have a crater that's younger than the smooth planes, then the impact happens already on smooth plane terrain that has a lower weight percent iron. Then as a result, the contrast in iron content will be more visible compared to the ICP case because of the lower weight percent iron, especially if we're in this scenario here to the right with a thicker layer of smooth planes that may result from multiple events, maybe. Obviously, in the smooth planes, especially in the northern smooth planes, we also have buried craters. Some of them have an enhancement that we're interested in right now. And for buried craters, we have two further scenarios possible.
2 minutes.
In one of them, the impact happens on an ICP-like terrain, followed by a smooth plane event. And in this case, we would expect a similar percentage of visible enhancements as in the ICP case, because the contrast would be mainly with the ICP unit surrounding the crater. But if the impact happens on a pre-existing smooth plane terrain, then we go back to, and followed by another, obviously, smooth plane event, because it's a buried crater, then we go back to the case of a more visible enhancement because the contrast is with the lower weight percent iron that's in the smooth planes. So to conclude, we started the study looking for a dynamo history, possibly for Mercury, but we didn't find any correlation between the age of craters and their enhancements, deficits, or strength of magnetization. So we're now exploring an alternative option that may explain the different numbers that we see between smooth planes and intercrater planes, which is impact delivered iron that would produce this iron content contrast, which would be more visible in the smooth planes where the lower weight percent iron, where we have a lower weight percent iron. And we believe that impacts on a pre-existing smooth plane layer may account for this larger number of craters with an enhancement that we see in the smooth planes. And with this, I think I'm done. Thank you.
Thank you. I'd like to ask all speakers to come to the podium now. Right, so go ahead, Lon.
Lon Hood, Arizona. This is a question for Isaac. Did you take into account planetary induction currents in your analysis?
Yes, both the curves I showed in the plots of solar wind dynamic pressure and magnetopause standoff distance take into account both core induction, which is a big effect for Mercury, as well as not in the plots I show, but there's also a weakening effect or an erosion of the magnetopause distance from reconnection, which would occur on some frequency.
Okay, good, because I didn't hear you mention it in the talk.
Yes, it is there. It would not change the conclusions even if Mercury did not have a large conducting core, because the change in the magnetopause distance is fractional compared to what the large solar wind dynamic pressure range is. But yes, I did include it.
Okay, I'll talk to you about it later.
Hi, Paul Sabo, UC Berkeley. Also have a question for Isaac. From the remnant magnetization, like how strong it is, does that give you any like upper limit for how much stronger the dynamo could have been?
That's a good question. I'm not too sure. One of the issues with coming up with these magnetization volumes for plots like what I showed is on the y-axis, I had the efficiency of the material to record a thermoremnant magnetization, which you might have seen spanned orders of magnitude. So that's one of the main parameters controlling the uncertainty in this problem. So potentially you could place an upper limit, but that would be the main source of the uncertainty, which kind of drives the allowable parameter space.
Okay, thank you.
Hi, Mario D'Amore from DLR Berlin. And this question is for Jeff about the, yep, I'm here. Yeah. The question is, maybe, I hope I didn't miss anything in your talk. It was really interesting. The question is, looking at the spectral range, did you try to compare to remote sensing data? Because this was perfectly in alignment with the data they used from Messenger and both spectrometer and the camera. As you know, the spectrometer was relatively featureless, let's say, and your experiment could really show how the change in carbon structure in the data on the surface could affect the refractance spectrum. So did you plan or did you try to match with remote sensing yet?
We haven't matched it by plotting the like MDIS or mass data along with our lab data yet. We've only done it by eye, but that's another future step to actually overlay the two and make sure that the curvatures that we see, especially in the UV vis side of things, are very subparallel to what we see in the messenger data.
Really interested in it, so I will wait for it. Yeah.
Okay, thank you.
Hi, Mallory Kinchek, Johns Hopkins, APL. My question, well, I have two questions. Feel free to cut me off if you need. For the last speaker, and I apologize if I missed it in your talk. Did you say what size craters you were looking at?
No, I didn't, but we looked at craters from 70 kilometers in diameter to 400 kilometers in diameter.
Okay, my follow-up question is, did you look at also the Caloris interior plains or just the northern smooth plains?
So the numbers that you saw in the slides are including even the Caloris interior and all the northern hemisphere between 40 degrees to 75 degrees north, because that's where the model is best, the magnetization thickness product model is best resolved. But the numbers are similar if we take out the Caloris region anyway.
Okay, thank you.
Alex Sankey, Arizona State University. A question for Jeff. So I've been thinking a lot about these amorphous carbon phases and trying to understand, would we expect them to be generated in the temperatures and pressures of, say, a large impact, and what would their structures look like? And it seems like a lot of the phases that we have from Earth samples are really just polycrystalline aggregates where the bond configurations are mixtures of like the sp2 and sp3 bonds of graphite and diamond. So first, I thought it was really interesting that your carbon black was actually becoming more crystalline after your weathering experiment as it was graphitizing. I think that's really kind of interesting. But my question is really, how amorphous is carbon black? Like, what does amorphous actually mean in that situation? I don't really have a good understanding of that.
I don't either. When you buy in the lab, it says amorphous carbon black. I guess the best way to get some XRD data on it and see if it, has any features. My guess is not. So I can't go any more than that.
Thank you.
Marco Zorik, IBGP. Questions for Isaac. A really interesting talk. Your main conclusion seemed to be that the present day strength of Mercury's dynamo is not sufficient to stand off the ancient solar wind. But is that only half true? isn't that only true for the sun, the day side of Mercury, and not for the night side?
Yes, so that's a good point. The rotation period would see surface material move through the day side on much, much shorter time scales than the long cooling times predicted for these large layers. So there are different effects that I didn't talk about that also account for how this variable IMF would affect not just the day side, but you are very right to point that out. Also, when you take into account more than first order effects, which I showed, there's also pile up at the day side, which gives a further enhancement of the magnetic field. So that's kind of what I was pointing out with saying that the magnetospheric field changes when you have solar wind forcing that brings the magnetopause to the surface. So those are things we're all taking into account.
Okay, thanks.
I have a question for the last speaker, actually. You mentioned that the carrier of your magnetization is impact related. I'm not a magnetics person, so excuse me if it's a stupid question, but how do you, what is the carrier really of the magnetization, and how does it survive the impact heat? I mean, you know, shouldn't you reset your magnetic signal that the impactor carries during the impact?
So this is something that we're looking at in a different study that's not this one that I presented. So I guess you'll have more answers about that later on once we finish up that study.
I also have a question for Jeff. You presented these 3 carbon varieties. Would you like to speculate which one is the most likely to occur on Mercury?
Or the different carbon. Right now, it's kind of maybe leaning a little bit towards the carbon black, or also maybe the anthracitic coal. Granted, there's never been any forests on Mercury to become coal, but it's that kind of, you know, process that where the carbon has gone through enough heating and pressure to create something that's more mineralogic like that than a graphitized carbon. The spectral features seem to favor either of those 2 modes, but we'll keep looking.
Catherine Johnson, UBC. Maybe I add just a clarification to answer your question, just so that it's clear. The hypothesis is that the impactor delivers iron, not delivers magnetized iron, right? So it's delivering iron that can then be magnetized in either an ancient or a present field. Yep.
There's still time for a couple of questions. Don't be shy.
Steve Harmon, Brown University. For the last speaker, have you compared your magnetized and less magnetized craters to compositional maps of the surface? You know, because iron does vary. You know, like the high magnesium region. Is there any?
So we had a look at the not specifically at craters magnetized or demagnetized, but like at the magnetization thickness product map in general. And it seems there's no correlation with the geochemical terrains or units.
And a question for Jeff. You know, there is this you know, outstanding kind of iron paradox that, you know, there is a couple of % iron in Mercury's surface, which we don't really know how it got there. But there's no veneer signal of iron being in the silicates, which is consistent with the low FO2. So we expect that. there's always this kind of niggling concern in my mind that, you know, maybe the FO2 wasn't as low as we think it is. The minerals did have a weight percent or two iron in them, and that the space weathering erased that. And you talked briefly, you said, oh, this is 1 billion years of space weathering to remove the iron signal from San Carlos. I guess my question is, if we speculate the minerals aren't San Carlos with, you know, Fo 90, but they're like Fo 98, how fast could we erase that with space weathering?
I think it could erase that pretty rapidly, especially when you consider not only the FeO, but you have carbon around, you have sulfur around. Each of these with the energy of an impact could change the iron and have it scavenged into sulfides and carbides, and you could pull that out of the olivine structure or the enstatite structure very rapidly. And it might be neat to see a comparison if we, like with San Carlos, think we've done 1 billion years, how long it might take to, if you have at least a little feature to kind of go by. And again, part of this works with the laser being at 1 micron, olivine having a 1 micron feature with the enstatite not having that feature. We might want to get a laser that works at maybe a UV wavelength or visible wavelength so that it's able to absorb the energy a little bit more efficiently. And we might be able to track and estimate how quickly it could lose that signature. Because right now you can calculate it, but there's a big debate at the efficiency of the laser energy to be absorbed compared to an impact being able to transit the energy kinetically to the material. So that's where it's kind of the big unknown, but we might be able to calibrate it somehow by using a different wavelength laser and focusing, you know, on that feature in the visible versus a near IR feature. So it might be possible.
Brooks Rosanich, University of Kentucky. I have a question for the third speaker. Considering what we saw in the fourth presentation, would the dynamo field still need to be 10 times stronger for Mercury if these were shallow, thin, high susceptibility deposits?
As your magnetized layer gets smaller, you require a stronger field to produce the same crustal signal at the same altitude it was measured at. This also discounts variations in magnetic mineralogy, so you have to factor that in as well. But if you assumed like the most like giving largest TRM efficiency for a thin layer, you would require a much stronger source field, whatever it would be.
Thank you.
Okay, I'll let anyone think if they have any last questions, but I will make an announcement here. There is a Mercury community meeting tonight, Tuesday, 5 to 6 p.m. in Grogan's Mills. It has a fun little flyer. I will note that this is an agenda-less meeting, as is required to be legally stated right now. Got you, Steve. So if you're enjoying the Mercury discussion, you want to make it a full day of Mercury, or at least most day of Mercury, go to the Mercury community meeting, and then to the Mercury posters, which are again tonight.
Okay, if there are no further questions, then let's thank the speakers again. Thank you very much. Okay, that brings us to our next speaker, Pommier et al. Title is Bonding of Sulfur in Highly Reduced Silicate Glasses and Melts, an Experimental and Multi-Probe Investigation.
Thank you.
significant amounts of sulfur have been detected in the highly reduced lavas at the surface of Mercury. And at these low oxygen fugacity conditions, sulfur is predominantly present as sulfide S2-. And we know that you can store more sulfide in these lavas as you decrease the oxygen fugacity. The motivation for our study is to investigate the bonding of sulfur in these highly reduced and complex silicate glasses and melts, because most previous works focused on more simple systems, binary, ternary, considered lower sulfur contents, or worked at higher oxygen fugacity conditions. And in particular, we have very little understanding of the transport properties of these materials, but they are needed if we want to model magma dynamics of reduced planetary interiors and of Mercury in particular. We adopted a multi-spectroscopic approach and did impedance spectroscopy measurements under pressure and temperature conditions relevant to Mercury to get access to electrical conductivity, which is a transport property that is related to the structure of these materials. We also performed silicon NMR spectroscopy and Raman spectroscopy to have a better understanding of the structural properties at the atomic scale. And we also conducted electron microscopy analysis on these materials to complement the chemical analysis of these samples. The starting materials are representative of the composition of the northern volcanic plains and are mostly ion-free. They are difficult to synthesize. It has to be done in a vacuum line using graphite capsules so that we can reach low oxygen fugacity conditions. In our case, we were at about 6 log units below the ion vesite buffer. And in total, we had 9 compositions, and sulfur varies between 0 to almost 5 weight%. And we have some traces of carbon because of the synthesis in graphite capsules. Impedance measurements were performed at 2 and 4 GPa and under a wide range of temperature conditions. You have here electrical conductivity as a function of inverse temperature for all the different samples. And what we see is that at low temperature, below the glass transition at about 700 Kelvin, we have a typical Arrhenian behavior. And the activation enthalpy E gives us information about who's governing the conduction mechanisms in these samples. And in our case, it is Na+ cations. It also means that alkaline earth cations and S2- are very minor contributors to the bulk electrical conductivity. Another important piece of information is that sulfur-rich glasses tend to have a higher conductivity than the sulfur-poor ones. It's not a systematic effect, and the reason is that our 9 compositions are not varied systematically. But this is consistent with the fact that sulfur improves the transport, the mobility of sodium cations. This has been shown before in non-reduced glasses. The other piece of information that is important here is that sulfur-rich glasses that contain more Ca2+, because we brought sulfur in our samples as CaS, tend to be more conductive than the other ones. And this is interesting because we know from the literature that Ca2+ tends to decrease conductivity. But here we see that it tends to be higher. So it suggests that S2- overcomes this typical impeding effect of Ca2+. The last important message from these electrical measurements regards the conductivity of the melt phase. At the time of quenching at high temperature, our samples were liquid plus forsterite crystals. And using 2-phase formalisms like the Hashing-Strickman upper bound, we can retrieve the conductivity of the melt phase from the bulk measurements if we know the proportion of crystals and melts and the conductivity of forsterite, which is known and was taken from the literature. And what we observe is that these melts are not conductive at all. Maximum is 2.2 Siemens per meter. And they are much more resistive than the hydrous aluminosilicate melts that have been widely studied in the literature at similar pressure and temperature conditions. Now, to really understand the structure of these glasses and melts at the atomic scale, we need to use other tools than impedance spectroscopy. And first, electron microscopy analysis revealed interesting results. The composition of the starting material and that of the retrieved samples was similar, which is always something good to observe. But more interestingly, we observed that we have some variations in the chemistry. You have here some traverses across a retrieved sample, and these plots are for different oxides as well as sulfur content. And what we see is that we have the formation of domains at the micrometer scale. And we think that these variations have no effect on the bulk measurements of electrical conductivity and of NMR. But it's interesting because it says something important about the structure of these materials. Our silicon NMR spectroscopy results are shown here, and they were performed on the starting glasses. The main band corresponds to a mixture of Q3 and Q4 species. And what is really interesting is the shoulder on the left-hand side of the peak that can be assigned pretty safely to SIS bonds based on the previous works by Hirai and Hayashi and coworkers on binary and ternary systems. This shift occurs at about -60 ppm. And this is confirmed with new results from Emily Fisher on different samples, reduced samples. And she has a poster later today at the Mercury session. We can go a bit further in the interpretation of these NMR results. And here this plot is flipped. The x-axis is flipped compared to the previous one. This shows a spectral decomposition of a typical NMR spectrum we had for one of our samples. And what we observe is that most sulfur is bonded to Si, and no or few sulfide atom is bridging between two Si atoms. And this is a new result compared to the previous work that had been performed, especially by Anzores and coworkers. So what NMR is telling us is that sulfur is bonded to Si, but on the other side, it's bonding to something else. And the answer comes from Raman spectroscopy analysis, which we performed on starting and quenched samples. Well, first, for bulk spectrum of one of our samples, we observed the typical bands for the structure of these glasses related to the SiO bonds. But more interestingly, we also have evidence for CAS and MGS components, as shown in the sample here, that agrees very well with the spectrum of aldamite, CAS. And one thing that is important to keep in mind is that Raman spectroscopy is not going to detect SIS bonds in these samples. The simple reason is that we have a spectral congestion with the CA-MGS components response. So we cannot see that. But what we saw doing Raman spectroscopy maps of our samples is the presence of clusters, sulfide-rich regions and sulfide-poor regions, which is in very good agreement with our electron microscopy results. So what NMR, Raman spectroscopy, is telling us is that sulfur is also bonded to Ca2 plus or Mg2 plus cations. Now, with all these different pieces of information, we really gain insight on the structure of these complex glasses. And if we think for a moment about the knowledge we have on sulfur-free systems, which have been widely studied in the literature, we know that alkaline earth elements are strong network modifiers. And this is according to this equation here in black. And we propose that in our glasses, we have alkaline earth sulfide, so CAS, MGS, that also act as network modifying cations according to this equation in red. And what happens is like we have some microsegregation of these network modifiers that are similar to what has been described in sulfur-free systems, except that we are here at the micrometer scale, not the nanometer scale. Now, the implications for young mercury are numerous. First, the fact that we have SIS bonds is going to change the way the magma ocean is going to crystallize. It will also affect other physical properties, such as viscosity of the magma ocean. And these studies actually are very consistent with the results of Megan Marther that show that adding sulfur is going to decrease the viscosity of the melt. And this is due to the depolymerizing effect of sulfur. Some magma oceans might generate some dynamos, as suggested previously for the moon, but for that, the melt has to be really conductive. So in the case of Mercury, if this were to happen in a big proto-Mercury magma ocean or a smaller one, then it would require the magma ocean to be mostly conductive because these melts are rather reduced. And finally, sulfides have a tremendously important role on the evolution of planet Mercury. And if you're interested in learning a bit more about what we did, there is later today a poster that I'll present about the evolution of a sulfur-bearing core, FeSIS, and including the effect of the hypothetical FeS sulfide rich at the CMB on the magmatic evolution of the planet. And also another poster on the electrical properties of alkaline earth sulfides used to develop electrical conductivity depth profile of the planet that will hopefully be tested soon with induction data from the BEPIC Colombo mission. And I thank you for your attention.
Thank you. The next speaker will be Dunningham, and the title of the presentation is Interior Models of Mercury and Conditions for Iron Snow Formation in an FeSSI-4.
Awesome, thank you. Good morning, everyone. My name is Abby Dunnigan. I am a first-year PhD student at Purdue University. But this morning, I will be talking about some work that I started as an undergraduate with interior models of Mercury and iron snow. To start out with, we know that Mercury has a large core, about 2,000 kilometers in size, as well as a weak axisymmetric magnetic field, at least measured in the present day. However, questions remain on the size of the inner core, as well as the mechanisms that occur in the outer core fluid to generate such a weak magnetic field from the surface. Specifically, both Mercury's large core and weak magnetic field are difficult to reconcile with the scaling laws of dynamo modeling. So one theory as to what drives this magnetic field is the process of iron snow. And iron snow is theorized to occur in the outer core fluid when the temperature drops just below the liquidus. And so when this happens, iron-rich solids can precipitate out in the form of iron snow. And when they precipitate out, they sink further into the core where they eventually remelt at greater depths. And this can drive compositionally convective flows in the deep interior. And at the same time, this sinking iron snow can push up buoyant light elements like sulfur. And this can create a compositional gradient within the snow layer. And consequently, this can also cause the region above the iron snow layer to be more saturated in sulfur than it was before. So iron snow is theorized to potentially generate Mercury's dynamo. And so we test the likelihood of this with interior structure models to answer the question of whether our most likely models actually contain iron snow. Our models are required to meet certain geophysical constraints for Mercury, such as its normalized moment of inertia, as well as the librational amplitude because of their dependence on the internal structure of the planet. Specifically, the libration amplitude can be used to calculate the ratio Cm over C, where Cm is the polar moment of inertia of the solid part of Mercury, including the mantle and the crust, while C is just the polar moment of inertia, which has more of a dependence on the core. And together, these can help us infer the state and the size of the interior. And in this work, we work with two sets of geophysical constraints, one of which is centered on a high moment of inertia, while the other is centered on a low moment of inertia. In this work, we model for various interior structures where some of them can create the feasible conditions for iron snow in the case of an iron sulfur silicon core. And so the core composition is one of the assumptions we make in our models where the core is mostly composed of iron with small amounts of sulfur and silicon. We assume silicon to be constant throughout the entire core, while we assume sulfur exists in just the outer core and it can vary with radius. And so this right here is a figure of a model that meets the high moment of inertia constraint. So we can see the different profiles for temperature, density, sulfur concentrations, as well as pressure. But what I want to point out is this diagram in the bottom right, because this shows the interior structure of this particular model. We also make note of a base of a thermally stratified layer, because another assumption we make is that the upper half of the outer core fluid is in a thermally stratified layer. We can also see that the inner core is between 500 and 600 kilometers in size. And then we also see an iron snow layer situated in the middle of the outer core fluid. It's between the inner core and the iron snow layer where we would expect compositionally convecting flows to be occurring. And then we also note that at the approximate radii of this snow layer, we see a slight uptick in sulfur concentrations. And this is just due to the sulfur being pushed up in the core while the iron snow sinks. And so for a given moment of inertia constraint, we are working with a wide range of models depending on our independent parameters. So these include the different silicon concentrations of our models, as well as different inner core sizes. So to account for the uncertainty in our constraints, we use a Monte Carlo study. So in this study, we randomly select a moment of inertia given its mean and uncertainty. Then we correct the CM/C ratio because of its dependence on moment of inertia. And then from there, we run a set of interior models that meet these particular constraints. And for that particular run of models, we track the counts of models that we get, as well as their properties for each silicon concentration and inner core size. Going back to the question of whether these models are consistent with Mercury or not, we first consider models that are thermally consistent with Mercury's evolution, which leads us to place constraints on the core mantle boundary temperatures to those between 1700 and 2100 Kelvin. And then from there, we look at models that contain iron snow layers that would allow for convective flows like the examples I mentioned before. So since we track the counts of models with different silicon concentrations and inner core sizes, we can track where the most counts of models occur for each Monte Carlo study. So in these plots, each rectangle represents a set of models that are calculated from those randomly selected constraints. And so we can kind of see where the most counts occur. And so in both cases, we see that models generally trend towards lower silicon concentrations. And then for the high moment of inertia, models tend to have smaller inner cores, while for the low moment of inertia, they tend to have larger inner cores, at least for the most part. Again, going back to whether these models are consistent with Mercury or not, we look at the sulfur concentrations in the cores. And so we kind of have to meet their constraint of a core composition of no more than about 2 weight %, and this is just due to the highly reducing conditions in which Mercury and its core formed. And so as a comparison to that, we take the volumetric averages to start out with of the sulfur inner models. And so we take the same samples from before and kind of take the means of those volumetric sulfur averages. And so we can see that in general, these mean values are above that 2 weight % limit. And just to make sure that there's not too much kind of variation in these samples, we also calculate the coefficients of variation and find that they imply little dispersion of sulfur contents around their means. And so in general, we can conclude from this that the models that contain iron snow layers just generally have too much sulfur in the core. And so this leads us to believe that iron snow may not be as likely as we thought as a dynamo mechanism for Mercury. As a test, if we ignore the iron snow hypothesis and limit models to those that meet the thermal and sulfur constraints, we still find some trends with moment of inertia. So for example, with the high moment of inertia, this time more models have higher silicon concentrations. And again, they have lower or smaller inner cores. And then conversely, for the low moment of inertia, they have lower silicon concentrations and again, larger inner cores. And so we can see that there's a little bit more overlap and variation than before, but we can still observe these general trends. Additionally, when we combine all of these models, we can revisualize the dependence of silicon concentrations and inner core sizes with moment of inertia. And we additionally show the trends of the mantle densities of our models with moment of inertia. So going from left to right, we see that there's a fairly tight linear correlation of mantle densities with MOI. We additionally see a linear trend for the silicon concentrations, although a little bit wider. And then we kind of see like a wider trend with the inner core sizes that's nonlinear. But at the very least for we can see different regimes of high and low inner cores or large and small for the low and high moment of inertia values. And so in general, this can provide implications for future constraints on the planet's moment of inertia. And so that can, in the future, be more telling of Mercury's interior. In conclusion, our results imply that iron snow is more so unlikely to drive Mercury's dynamo. So this means we should probably look towards other explanations, such as a thermally stratified layer, or sorry, just a stably stratified layer at the top of the core or interactions with the solar wind, for example. Our results also provide implications for future geophysical measurements of the planet. So for example, if Bepi-Colombo measures a more constrained or newer moment of inertia, this could have implications for the core structure, the core composition, as well as properties like mantle densities. And that was my talk. I will be happy to take any questions during the Q&A.
Thank you very much.
We come to our next speaker, Errol Deutsch, and coworkers, and the title of the presentation is The Role of Slopes in Keeping Hollows Alive on Mercury. Ariel.
Before I begin, I also want to thank my collaborators, Valentin Bickel and Dave Blewett, who have been a lot of fun to work with thinking about why hollows form and evolve on Mercury. So as a brief introduction, hollows are these small, shallow depressions that are found on Mercury, and they're morphologically characterized by rounded, irregular outlines and flat floors. We don't understand exactly how they form, but presumably they undergo some sort of sequence of development, and a potential life stage is illustrated here. And so, for example, we think that small hollows initially form by some volatile bearing phase being lost from the host material, and that causes the material to weaken and crumble and collapse. And then over time, that hollow can continue to grow as more volatiles are lost, or as the pit continues to expand by something maybe like lateral scarp retreat. Eventually, that activity would slow down as your volatile sources are depleted, or maybe you accumulate some sort of protective lag deposit that prevents further volatiles from being lost. And then eventually, hollows can sort of fade away into the background as space weathering processes take over. And to date, 3 major stages of hollows have been observed. Stage 1 hollows are characterized by well-defined morphologies and also high visible reflectance exteriors and interiors usually. These are interpreted to be early on in development and even potentially active today. Stage 2 hollows have more muted morphologies, and they also tend to lack continuous high reflectance halos, and they're interpreted to be potentially further along in development or inactive. And then finally, stage 3 hollows are really muted. They pretty much blend into the background terrain, and they're interpreted to be potentially expired hollows. Recently, we published a pair of companion papers where we trained a neural network to automatically detect hollows in messenger NAC images. And we're excited to share this publicly available database now online. And in the second paper, we looked at a subset of this polygon-based data to look at the global distribution and characteristics of these different stages of hollows. And we saw that globally, there wasn't a significant difference in where we were finding these different stage 1 versus stage 2 hollows. However, in different local settings, we were seeing some differences such that stage 1 hollows were often located at relatively higher elevations and steeper slopes than nearby stage 2 hollows. And so for this project, we're interested in these different local settings. So here we're asking what factors affect hollow evolutionary sequences in local environments. So to address this question, we're analyzing local hollow-rich environments that we identified in the Hornet dataset, which you can see plotted here on a global map. Each black cross represents a human-verified detection of a hollow from the Hornet dataset. And we've chosen study areas based on the fact that they host both stage 1 and stage 2 hollows, and also they are covered by high-resolution DTMs. So you can see the coverage of the specific DTMs we've analyzed so far. We have 2 in Radit-Lati Basin and also 2 in Praxiteles. We know there are other high-resolution DTMs that cover different hollow-bearing environments, so we're looking forward to including those next in our project. So for each DTM, we trace the hollows and we measure different properties, including surface area, elongation, elevation, slope, and azimuth or direction of slope. And then we classify the hollows based on our stage classification scheme. You can see that stage 1 hollows are colored here in green and stage 2 are in yellow. And we have about 1,000 polygons right now for this analysis. The stages are classified using the classification scheme we presented in one of our companion papers. But again, stage 1 are characterized by relatively crisper morphologies and high reflectance anomalies. Stage 2 look more muted and they tend to lack a continuous high reflectance ring. When possible, we also measure the depths of hollows using the DTMs. This is a little bit challenging because of the relative scale of the DTMs and the hollows themselves. So for right now, we have depth measurements for about 4% of the total study population. To get depths, what we do is measure 4 intersecting profiles across the hollow floor and measure mean and median. It's important to note that the vertical scale of the DTMs is the same order of magnitude of the depth measurements, so there's some uncertainty to be aware of. Okay, so for some results, We're seeing that in regions with level terrain, stage 1 and stage 2 hollows are commonly found together. They occupy a similar proportion of this population, about half and half, although typically stage 1 covers more surface area in total. But in regions with topography, we see that the relative proportion of stage 1 hollows and the area covered by stage 1 hollows both increase. And so we think this is telling us something about the initial distribution of the volatile bearing material, because the topography that's captured in this measurement is the relict peak ring structures of the 2 basins we're studying. And so perhaps those areas contain more volatile rich material or contained more volatile rich material than the adjacent basin floors. In addition to elevation, we also looked at slope, and we're seeing that the steepest slopes tend to host stage 1 rather than stage 2 hollows. And perhaps this is suggesting that slopes play an important role in keeping hollows active on Mercury, because the mass wasting that can occur on slopes can both expose more volatiles to the surface, and also it could inhibit the development of a protective lag deposit. Right now, we don't see a major correlation between hollow shape and the steepness of slope. Shape here is quantified by an elongation factor, which is the ratio of the short axis to the long axis of a bounding box that encapsulates the polygon or the hollow. So this suggests that there's some other factor rather than steepness of slope that's governing hollow shape. We do, though, see a slight correlation with hollow shape and direction of slope, such that the most elongated hollows appear on sun-facing slopes. And furthermore, we see that the biggest hollows are also present on sun-facing slopes typically. And this is consistent with a number of other independent observations suggesting that insulation is a primary driver of hollow growth and potentially elongation too. Also, we think that maybe the direction of slope is having an influence on the direction of hollow growth, because we see that when located on steep slopes, hollows tend to orient perpendicular to the direction of that gradient. You can see a couple examples here, but the interpretation is that direction of the gradient can affect the development of hollow shapes. And finally, we looked at our depth measurements for hollows where that was possible, and we see that there's no significant difference between stage 1 and stage 2 depths, acknowledging that we only have a limited number of samples here. So this suggests that if stage 2 hollows do have a protective lag deposit, then it is less than that vertical uncertainty of the DTM, which is about 20 meters. We can derive a relationship between hollow depth for these particular hollows and their surface area, and that's what's plotted here, suggesting that hollows grow both in the lateral direction and also in the vertical direction over time. And then you can apply this to our new polygon-based database to get some sort of constraint on how much material was lost altogether in the formation of hollows, which we've constrained to, thank you, a decameter thick global equivalent layer of material on Mercury. This is an order of magnitude higher than previously suggested, which is primarily due to the fact that we now have many more detections of hollows presented in the Bickel paper, thanks to Hornet. So in conclusion, we're finding that local environments seem to have an important role in the development and evolution of hollows. Specifically, we saw that stage 1 hollows are more common than stage 2 hollows on slopes, suggesting slopes may be important in keeping them active, keeping them alive on Mercury. On slopes, hollows tend to orient in the downslope direction. And on sun-facing slopes, hollows tend to be larger and more elongated. We don't see a significant difference in depths right now, suggesting that if there are lag deposits in stage 2, they're less than 20 meters thick, which I think we thought maybe anyway. And then we can use these new depth area relationships to get some sort of constraints on the material lost during the formation. We're working on including other hollow rich areas in our analysis with different DTMs. And of course, like everyone else in the room, we're really looking forward to more Bepi-Colombo data to continue learning about hollows. Thank you.
Thank you, Ariel. So that brings us to the last presentation in this session, which will be given by Lauren Joswiak, and the title is Uncovering Mercury's Missing Pyroclastic Vents.
Thank you. Ma'am? Okay. Thank you. And thank you everyone for staying for the last talk of the Mercury session. Today, I'm going to first convince you that we actually have a population of missing vents, which on its face is a little bit of an absurd proposition. The planet doesn't owe us anything, so why should we think something is missing? But I will, in fact, show you why we think something's missing and then how we're going about finding it. So to start off, we're going to talk about a feature that we have not yet talked about today in the Mercury session, but we're talking about Mercury's explosive volcanic deposits, and they actually come in two morphologic parts, and it's really important for this study to understand that. The first part is the actual physical topographic depression. We call this the vent. This is from which material has been erupted, and then you have a subsidence forming this crater. They can be elongated, they can be more pit-like. We have a wide range of morphologies. Then associated with this, there is the bright deposit. This is called the facula. So if you look at the IAU nomenclature, the facula actually refers to this bright spot deposit. And you can see it here. It shows up orange in the Mercury false color mosaic data. This is how we first identified them. And this is thought to be correlated with the pyroclastic material that has been erupted from this vent. What's really exciting is that we did not expect to see these features on Mercury. It was thought that when Mercury formed, it formed so close to the sun that there would not be a significant volatile population in the interior. And you need that in order to drive explosive volcanic eruptions. You need gas fractions most of the time in excess of 70%. So really very gas rich. And so this is a very exciting discovery. We mapped them across the surface of Mercury. And depending on which catalog you use, we have a population of about 150 of these features, which we will be calling vents, but again, there really are two different parts to the morphology. So what we wanted to figure out is we wanted to figure out if these really are reflecting interior volatile processes, when did they form in the history of Mercury? And so this is a project that I've been working on for a number of years, and we actually have a paper that is in press currently led by Maria Leondasi, which is looking at the ages of the vents. And I won't go too much into detail for that here, but what you need to know is we looked at the degradation of the vents using a process that is comparable to the crater degradation. We put together a series for the actual physical vent morphologies, and the Morella analysis of the masks data looking at the degradation of the facula. And what she found was that the two correlate, the two correlate really nicely, and you can see this trend here, where as you get to more and more degraded vents, you get less and less of a signature of the facula. And we think that this is due to space weathering, and this process happens at a relatively fast timescale commensurate with general space weathering on Mercury, such that for the majority of vents that we see with facula, we think most of them must have had their most recent eruption within the past, say, billion years or maybe 1.5 billion years, which is really very recently in Mercury's future, or in Mercury's recent geologic past. There we go. So if we put it together on a timeline of Mercury's history with the main geologic periods, we have effusive volcanism way here in the earliest portions of Mercury's history when it was hot. That ceased largely around 3.6 billion years ago. We go into this protracted period of contraction where we have general thrust faulting activity. And then right here at the end, we pop up with our current population of explosive volcanic vents. And that's really interesting. It's really interesting to tell us something about what the volatiles in the interior might be doing. But it's also really weird. Why was there almost 1.5 billion or 2 billion years of period of time in Mercury's history where there was not explosive volcanic activity? And so this was sort of a niggling question in the back of my mind as we were putting together this work. And it led to this question, are we missing something? Are we actually missing in our records the vents? So in order to understand that, we need to look at how we actually mapped these features. So we're going to do a little bit of a history tour. So this is the very first global distribution of the vents. This is from Kerber et al. 2011. This is from flyby data exclusively. And you can see we have a population of about 25 features across the surface of Mercury. And what's important to note for these features is that they had to be large enough and bright enough and weird enough that they were mapped during the flybys, and we had to cover them during the flybys. So this is, of course, going to be a non-exhaustive data set because of that. Time goes on, we get more and more data. We're now going to pop ahead to the end of the MESSENGER mission. So this is a data set that I published in 2018. And what's important to note here is that this data set focuses specifically on those topographic depressions. We are looking just at places where there was an actual physical expression of the explosive volcanism, not necessarily just at the facula. And so this database drew on the Kerber data set, it drew on a data set from Tim Gouge in 2014, and it also drew heavily on a data set put together by Rebecca Thomas also in 2014, which looked exclusively at places where we had this color anomaly, this false color anomaly. We call it the red spot. They're actually kind of yellowish orange. But what she noticed in that data set was not every red spot had a topographic depression associated with it. Well, for this study, I was looking specifically at that, so I focused only on places where we had depressions. Move along. This is the current best estimate. This is from Peg et al. In 2021, and that used a combination of my data set. It used a combination of Rebecca's data set, digging a little bit more into higher resolution data that we had from the Adam Messenger, and it put together this database. And what's important to note is that, so it's derived from a combination of all existing databases. It focused on identifying compound vents. So it's a slightly different flavor of vent style and includes previous identifications of red spots. And most importantly, 90% of the features in this data set had a red spot facula associated with it. So if we put that together with our degradation from the original part, what we are seeing is that 90% of the features that we're focusing on are the ones that are being erased within, say, 1.5 billion years. So there is reason to think that the current databases are not capturing anything that does not have a red spot because we didn't know how to find them. And this gets back to the question of what should a planet have on its surface? And during the course of exploration, you need to continually reevaluate what you're learning about these features. So we went in with the hypothesis, are there features that look like vents that do not have a red spot? So that's what we're going after. We're going after this period of history where we're going to look for very degraded vents. We are not going to use any color data to try to find them. So we're calling this the new search for old vents, and we're using targeted search areas. Mercury, although it's a small planet, there's still a lot of space there. It's a very big space to try and search. So we're doing targeted search areas. We know that the majority of vents are located near faults and in impact craters. So I'm showing here are the buffered impact craters that we're looking at. These are craters within 100 kilometers of the edges of smooth plains deposits. And this is where my co-author Erica Jowan and I have been focusing our efforts, is looking for features in these craters. And it's great because it's really easy to find weird things inside craters because you generally know what a crater floor should look like. In coordination with this, Hans Bernhardt and his team at Mercats have been mapping the small shortening structures, the thrust faults, which is the other common location where we see explosive volcanic deposits. And that's what I'm going to be showing you for our mapping. These are kind of what we're looking for. They're not really charismatic. I will put it that way. We've seen a lot of the charismatic vents, but we did establish a series of geomorphic criteria to identify what could be a candidate old vent. They have to be elongated to quasi-circular topographic depressions located inside an impact crater or near a thrust fault, and the relative size has to tell you something that it's not a secondary crater. If there are a bunch of small things in a chain, it's probably a secondary chain. It's probably not a series of small vents. Within the quasi-circular features, the ones where maybe it could be a degraded impact structure or maybe not, we look at the depth to diameter ratio, we look at the characteristic of the floor profile. At these small sizes, it probably should be bowl-shaped. If it's an impact crater, it shouldn't have a very, very flat floor if it's a vent. So those are our main criteria for distinguishing these. Here are some of the features that we've started to find, and you can see a lot of them are elongated, they're weird, they're definitely not impact craters, they're probably explosive volcanic, some of them are probably not. We haven't fully distinguished all of them yet, but we're trying to get everything that could possibly be volcanic in nature first. This is, as of when I had to turn the slides in, the updated population. You can see we've mapped just over half the planet in the impact craters. Those are shown in red. The white are from the Mercats global study, and there are a lot of them. If we compare just our study against the PEG, you can see that we are still identifying main volcanic regions around Caloris in these the southern blue plains. These same areas where we know we have volcanic features, we're now seeing even more of them. So what are we doing? We're finishing this data set. It's almost done. We have a little 15-degree sliver left to finish mapping. And then what we're going to do is we're going to swap sides of the planet and reevaluate, and we're going to use the confidence interval criteria established by PEG to put together a final catalog of new old vents with associated confidence to hopefully hand off to the BEPI team and figure out what's going on here. And for our interior composition folks to figure out how we can have explosive volcanism throughout Mercury's history, because now really looks like it has existed throughout Mercury's history. Thank you.
Thank you. So I would like to please have the speakers up on the podium for the discussion and Q&A session. Okay. Please come up to the microphone and state your affiliation, and then.
Hi, Megan Mauser, Momentum, NASA JSC. So this is a question for Anne. I'm very excited about your work, obviously. But one of the things that we had tossed around when we were looking at the reduction in the viscosity was potentially silicon being in a slightly lower valence state at these reducing conditions. Is that something that you're able to confirm or look at in your work?
Not in our glasses. We were at extremely reduced conditions. The thing that is interesting for me related to your viscosity measurements is that the bonding energy between SIS and SIO are very different, and it's much weaker for SIS. So I'm not sure you need to invoke a change in valence. I think just looking at the energy bonds between the different atoms might explain the effect that you saw on the viscosity of these liquids. I think you were at slightly more oxidizing conditions than where we were, but probably close to
IW -4?
Yes, okay, we are at -5, 6.
Okay.
But close enough, I think. So
Okay.
yeah.
What pressures were you running these at?
2 and 4 GPa.
Okay. And did you see any like distinct changes with the bonding between those two pressure conditions?
No, we didn't.
Okay.
And for the impedance spectroscopy, which would be sensitive to these major changes at the atomic scale, we had a completely negligible effect between 2 and 4 GPa.
Okay. Yeah, that tracks, because it was really like we didn't see a lot of changes within the viscosity behavior in that sulfur bearing one compared to the sulfur free, where there were distinct changes in the viscosity. So it's great to see it all come together. We're figuring it out.
Yes, exactly.
Thank you.
Hi, Caitlin Frizzell, Arizona State University. I have 2 questions for Ariel, if that's okay. The first one is just that with the hollows, do we happen to have any analogs of hollows, either terrestrial or elsewhere in the solar system, that could give us any clue about like the evolution timescales and morphologies that we would expect?
There aren't exact counterparts that have been observed, although there are some features that look somewhat similar on other, for example, like comets people have suggested, or maybe some icy moons. That might give you a sense of how they form, but for timescales, it might be a little bit different. Timescales is something I think still important to constrain for hollows, and presumably could also change depending on the local environment, like how volatile rich that initial source was, and then also the processes that are degrading away. Yeah.
Cool, thank you. My second question is, do you find any correlation between the distribution of hollows and latitude that could indicate some sort of like evolution driven by Mercury's slow rotation?
Yeah, so there are some geographical patterns, and they're discussed at length in the Bickel et al. Paper, but also in some earlier work too by Dave Blewett and Rebecca Thomas. And the main observation is that the density of hollows seems to be highest at hot pole longitudes, and then also near the equator. So that's a primary observation that maybe insulation is a big driver of hollow growth.
All right, thank you so much.
Hi, my name is Shay, and I'm from Western Washington University, and I had a question for the 4th speaker.
From a morphological standpoint, how can we differentiate between hollows and these vents?
That's a really great question. Actually, something that Ariel and I have talked about doing, particularly when we are at these very heavily degraded states where you can no longer rely on something like masks data, because in mask data, it's super clear. Hollows are blue, these are orange. But this scale is one of the biggest things, is that the smallest of our vents overlap with the largest of the hollows. I also suspect that in the depth to diameter ratio, we'll see something pretty clear. Hollows tend to be much shallower than vents. Vents are typically a few tens to hundreds of meters, if not kilometers deep. So that's something, and we're looking towards a new DTM, which I have been assured is going to be published sometime this spring. Honest, I'm looking at you. Where but the depth to diameter ratio is also going to be another key. Also location. So Ariel was talking about these hollows typically being located in areas of higher slopes for the younger ones, but vents typically are not located there. They're generally just hanging out in the middle of crater floors or where or adjacent to where peaks or peak rings might be, but we don't tend to see them on sloped surfaces per se.
Thank you.
Hi, Will Nelson, University of Hawaii at Mount No for Pommier. I was just curious how you maintained your reducing conditions in both of your experimental setups, and yeah, because it's so reducing.
Yes, that's a good point. So first, the time scale of the experiments is quite short to do the electrical measurements in the multi-anvil press. So that obviously helps with the kinetics of the reactions. The other thing is that the cell assembly we use that I've been developing in the last few years with my colleague at ASU, Kurt Leinen-Weber, is used so that we keep some relatively reducing conditions. It's not buffered, but we are not changing the conditions tremendously compared to the starting materials. And how we know that is with the post-experiment analysis, especially the electron microscopy analysis, that show that, for example, ions stayed as ion metal if we are studying metals and we are not forming FeO or Fe2O3. So these types of things really help. I think having the metallic discs that are used as my electrodes for these measurements also helps maintaining some relatively reducing conditions. Yeah.
Thank you.
This is Hannes Bernhard, University of Maryland. This is another one for Ariel. You mentioned decameters or decameter global equivalence layer of volatile. Is that just based on the volume? I assume that's not just from the volume missing from the hollows themselves, but you're extrapolating that hollow thick layer about 20 meters to the entirety of the globe. Is that just how you came up with the global equivalence layer value?
So two things. One, it is volatile bearing material. So we're not saying that's pure volatiles, just for clarity. Yeah, so it's calculated by looking at the depth and area of the hollows we've measured. So we have areas of all the polygons that were detected by Hornet. We now have that depth to area relationship from the curve. So based on where your area plots on that curve, we extrapolate what the depth might be. And then based on that total volume, we stretch it over the globe of Mercury to get a global equivalent layer.
So where did that stuff come from?
And where did it go? I think also is a bigger
Or how much of that is left in those areas we don't see hollows? We might assume that layer is still retained, probably, or the hollows have been there, gassed it out, and have long been gone, right? But so would you say the former or the latter would be more common throughout the entire surface away from the hollows that we see today? Is there more area where we still preserve that layer in the subsurface, or do you think in most other places it's already long gone?
Yeah, that's a good question. I'm not sure I'm conceptually actually visualizing a layer, by the way. Like, I don't want to propose that there was a particular volatile rich layer across the globe. There are areas that maybe had volatiles in the material and that led to the hollow growth. And I think that is going to be patchy around the globe, depending on your source material, depending on the impact cratering history and what's being brought closer to the surface. I'm not sure. Sorry, your second part of the question, is there more? I think that, yeah, I think hollows might still be able to form and evolve today based on the fact that some of them still do have those high reflectance characteristics, indicating they might be relatively young. There's also been some work by Emerson, I'm sorry, I don't know how to say his last name, Spryer, suggesting that maybe there have been some reflectance changes in hollows, like on messenger timescales. And I think that even if an area has been inactive for some time, then potentially you could reactivate hollows if, I don't know, maybe by some bombardment process. So, yeah.
We have a couple of online questions. First, David Rothery at the Open University in UK asks, for Lauren, great work. Did you say old vents have lower depth to diameter ratio than impact craters? Young vents are relatively deep, so you must be seeing a lot of infilling as well as softening of form.
Yes, we are. I also would not fully stake our depth to diameter ratios yet. It is a qualitative assessment compared with impact craters. However, we are hoping once those new data get out there to actually really firmly put it out there. But yes, to Dave's point is younger vents tend to be really very deep, and we are seeing a significant amount of infilling in these due to any number of processes that have happened.
I'm Kenji Kurosaki from Kobe University. I have a question for the Danigan because you said about the iron snowing. If the iron has snow down to the core, and then gravitational potential should be released, and then the planet and then the Mercury should be reheated. So in that case, the thermal evolution should be different from should be different. So could you comment on the consistency with the thermal evolution of the Mercury if we considering the iron snowing?
Yeah, so that's a good question. Yeah, I guess so. These models are technically for the present day structure of Mercury, that we don't really model for the evolution. I guess, yeah, I guess so. The iron snow process, I think, happens relatively fast, where the iron snow sinks and then remelts at a greater depth. And I think this can potentially contribute to inner core crystallization, but I don't know if it would really create like large changes over like long periods of time, for example. I guess it depends if it occurs today. I guess it depends on how long lasting of a process it is.
Okay, thank you very much.
We have another question online from Sander Goosens at NASA Goddard for Abby. Great talk. From the interior model example slide, it looked like the inner core was pure iron. Is that the case for all models? And if so, would that drive core size to fit the moment of inertia versus using an iron silicate solid and liquid core?
Yeah, actually, yeah. So I guess just to clarify, I don't know if I mentioned this in the talk, but we do assume an iron silicon inner core. So I guess that's from the assumption that silicon partitions equally between solid and liquid iron. So the inner core is has silicon in it as well.
Steve Parman Brown, Anne, I'm really curious about sodium. How does sodium bond in the melt structure, and does the electrical conductivity that you're saying that it's carrying the charge, speculation on how sodium is bonded?
Yeah, that's a good point. So sodium in these in silicate glasses and melts is a network modifier. And the Coulombic interactions with sulfur are extremely weak because of the difference in sizes. So sodium replacing oxygen with sulfide is going to help in enhancing, as a consequence, the mobility of sodium. So that's why we have these high conductivities for sodium-rich glasses and melts. in terms of the bonding, it's not affecting anything related to the SIS bonds or the CA-MGS components we observed. So if we were studying glasses with a lower sodium content, which could also be relevant to mercury, we would probably have an even lower conductivity, but we would still see these SIS bonds and CA-MGS species. So it wouldn't affect the structure significantly, I think.
But do you think it's bonded with sulfur in kind of a, you know, silicon sulfur sodium bond, or is it kind of divorced from that?
It is not
business
related to it, yes. And if I recall correctly, in the Anzures et al. Paper, there were some NAS bonds detected at specific bands, and we didn't see that with Raman spectroscopy. I think they were observed in this other study at slightly more oxidizing conditions. Here we were really reduced, so we didn't expect seeing them, but the bonds are so weak that it's not a surprise to us. Yeah.
Cool, thanks.
Thanks.
Alex Sankey, Arizona State University. I have a question for Lauren. So thank you all for your talks, by the way. So I'm trying to think about a specific mechanism that could actually erase this spectral signature of these faculae from a compositional standpoint. So I'm wondering if you have any thoughts about that. And sort of a second part of the question is if you see any spatial correlation between your new old vents and low reflectance material, which might be a source of like a veneer, space weather, darkening kind of material.
Okay, so for the first question, that's a really great question. And partially, we don't know because we don't actually know what this material is. We suspect that some carbon species and some sulfur species are driving this type of eruption, but we don't actually know what that means for the composition of the deposit, except that it is different. So as to what is actually the specific chemical weathering, that I cannot speculate. We think a lot of it is physical weathering because we do actually see a couple of vents, and one that in particular is springing to mind are the vents in the crater Kipling, where morphologically they're rather fresh. They're compound vents, but there is an even fresher crater. I believe it's actually one of the Hokusai rays just cuts right across it. And so you don't really see in any of the masks data the composition associated with it. So it's possible that this just kind of surface impact regolith gardening can lead to a degradation of that deposit strength, but there are likely other compositional pathways as well. We just can't really say, or I don't feel comfortable saying what they are right now. As for the second question, the distribution, see, yes, and we do see the vents all over the surface. We don't usually see them in smooth plains deposits. Even in this new study, we really don't see them creeping into the northern plains all that much, which is curious. In the southern low reflectance plains material, we have a huge boom of them. We also see them in some of the larger craters like Radulati, Rachmaninoff, where we have the blue plains material inside the crater as well. And we see a lot of vents there, but it's not an exclusive relationship. Similar to hollows, we tend to see vents near hollows, but not enough to say that there's a causal relationship in the location yet.
Thank you.
Francis McCubbin, NASA Johnson Space Center. I've got a question for Anne. So first of all, that was a really incredible study, and the discovery of the sulfur silicon bonding is really cool. Do you anticipate any activity composition effects on, you know, whether you get olivine versus pyroxene stability with this, or is it going to be a net neutral thing since the other end's bonding with something like magnesium or calcium?
That's a very good question, and I don't have the data to answer that with confidence. So this motivates a lot of studies. And I know that some groups like Olivier Namur and others are now studying the crystallization of a Mercury and magma ocean. And I hope they'll take that into account, and let's see what they observe. But yeah, I expect it's going to change things because, you know, if you crystallize olivine or OPX, it's not going to be the same story in the end. Definitely for the physical properties, it will have an effect too. So more work to do, I guess.
Excellent. Thank you.
Hello, my name is Ruth Gale from Pomona College, and this is a question for Dr. Ariel Deutsch, if that's how you pronounce your last name. With Hornet, I assume it's some sort of convolution neural network. Do you actually probe the hidden layers to see like what morphological features the network is like identifying?
Do we probe the hidden layers?
Yeah, so like you can like after it like identifies whether or not like or like what stage of hollow it is, typically like within the hidden layer, it has some sort of complexity with which it's like actually identifying some hollow. So if have you just used it as like identification methods, or have you actually like probed those hidden layers?
Yeah, so the way we did it was as an identification of the hollows in the NAC data set. And then we did a human verification of all the detections. We did initially think of, or actually try to train it based on the different stages, but initially there wasn't enough input or training data to have the different stages because we had been overwhelmed with basically just stage 1 types of hollows. That's what initially like drew researchers to study hollows in the first place. They looked bright, they looked interesting. And yeah, so part of the training data set was only visible images, although they were visually augmented in a variety of ways so that Hornet could learn under different conditions.
Thanks.
And I can't see because the lights, but I think Valentin might be here too. Valentin Bickel also ran that training. And so if you have more questions about that, then I'm sure he'd be happy to answer.
Nice, thank you.
You're welcome. Thank you.
Thank you. I don't see any further questions, so that brings us to the end of the session. So please give a big round of applause to the four speakers. Sorry. Thank you very much, and see you in another session.